longitudinal girders, cross girders, piers, anchor frames, footing, and not piers, it should be piles, and the traffic lights, everything, concrete slab, everything is in there. So you can see on the top, you have one red box in here, then you have a blue box in there, then you have a pink one on the bottom. The red box is the one, the girder and the deck and whatever it attached to the deck. We call that section, those elements together in a bridge, we call a superstructure. Yeah. Then the cross beams and then the columns, and that part we call substructure. And then you got your foundation. And this is how bridges, which have very, very, very simple. You got a superstructure, you got a substructure, you got a foundation. So not a big deal. So then if you are designing a bridge, you design your superstructure, you design your substructure, design your foundation, bridge design is finished. Yeah, simple as that. So we see in detail what are these superstructure elements we call the bridge deck? What are those bridge deck? What sort of bridge decks you can encounter? How all these elements assemble together? How are they going to perform together to support the bridge we are designing for, mainly for traffic. We design for people to walk, and sometimes we design for people to play as well, and mainly for traffic. So how are we going to assemble them together to have a traffic, the denominated traffic loads on the bridge? And any question in this one? I'm not going to explain in detail about the cross beam and other thing and the piers, all this assembled thing at the moment. The superstructure, you got a deck, you got a beam, you got a barrier, you got a bridge joint. You can't see bridge joint in here. And then I said in here, between the superstructure and substructure, I put an arrow and I put a bearing. This is one of the most important thing on the bridge. You can see you got a significantly massive bridge superstructure. You will see during the presentation. You got a massive substructures as well. You will see them. They are scale. But you're going to link them together by a very small piece of rubber or rubber combination with metal, what we call bearing. Then the substructure and superstructure will be linked together by this bearing. If your bearing is failed on a bridge, it's look like exactly like your hand. You can move around in a joint, we call ligament or something. Is damaged. So then your hand or your hand or leg or anything, it can't function. Sometimes if you get like a spinal cord, if it is break, you will be paralyzed. The bridge bearing do exactly the same job in a bridge. Yeah, another thing, because of that, you need to pay really big attention the way you design your bridge bearing, the way you construct that one. Yeah, because this fellow is going to link this massive superstructure and substructure together. You will see that one through the presentation. Please keep that one in the mind at the beginning of our presentation. And of course, the foundation, put-in and piles, every engineer knows about it. I think you have been involved with designing many of those things, even columns, even beams, decks, slabs. Yeah, it's not a problem. The next one, this next slide, I'm having a bridge elevation. The bridge elevation, I got one of the drawing. This is about 663 meter long bridge. And in this bridge, you can see there are so many information is in there. Don't worry too much about this information at the moment. You can see this shape of this the slopes. It's going flat, is going up. You can see my mouse is moving. Yeah, this is in the middle, look like they call normal water level. That means it's a creek in here. And then you can see I got a box out in here. That one, say 100-year ARI flood level. here. And you can see above this line, I have another straight line go all the way across. That is the bridge soffit. Yeah. So on your left-hand corner, you can see on this elevation, I have another box. Yeah, there's another vertical arrow here, but you might not see it properly, but there's a vertical arrow in here. We have a shared path. The minimum clearance is 2.9. My bridge soffit, I had to make sure that I put that one above that one. So this bridge elevation, you can see, looks like it's climbing up. It's climbing up. It's climbing up to make sure that we get this elevation right, to make sure that we put our bridge above the flood. So in that, the elevation, in addition to that, you can see the vertical dotted line. They are piles. And then you can see footings, you can see columns, you can see the span length. We mark this one in here. In this bridge, the typical span is the 34.1. On your back, you can see the, I don't know whether you can read it, approach slab, the barriers, and then batters and things. Yeah. On the bottom is give all the levels, something. This is how we're going to present a bridge in elevation. I know you draw the elevation in a building, elevation in a retaining wall, anything, the engineers draw plan and elevation and reinforcement detail, etc. The same way in the bridge also we have, but we put all this information in the bridge elevation. The next slide, I got the same bridge plan because I can't put both them together because you can't read them. In this one, you can see the layout. In the layout where you got a dot blue and red, these are boreholes. At this location, you can see footing and the piles. And in addition to that, you can see this bridge, the lines we draw is not perpendicular to the bridge. The line, adjacent line is the bridge outline. And in the around at the right hand, sorry, in your left hand corner, you can see the like arrows we draw here. That is the batter. And you can see the contours in here. You can read that one. You got a contours in here. And so much information in there. The bottom line is so much information in there. Another thing, you can see the riprap is around as well. So all those things we can put it together because we get the detailed survey like a GPS and all this 3D modeling. Now we can combine together, we can develop this plan. This provides so much of information. Don't worry about at the moment, this information. Just see the way we presented this one in here. You can see when you are building a bridge, because in this one, you can see there was elevation, there is a batter down here. Because of that, when you build a bridge in a higher level, so how we going to match both grounds together? Yeah, because otherwise you can't build a bridge here and then leave the ground without stabilizing that ground, then it will fail. The bridge will not fail, but surrounding in bridge area, the road and other thing will be failed, then automatically you can't access the bridge. No point having a bridge if you can't access that one. So because of that, all this element, we're going to put it in the here, but we're going to see them in detail. Any question up to now? No, I know your question is because you're going to tell me, mate, we can't read anything, it's too small. Yeah, anyway. Now I'm going to a bridge cross section. This bridge cross section, I'm going to show you, this is one of the most common bridges in Australia, but it's a similar one we use in the other part of the world as well. This is the we call Super T girder bridge. The bridge we talk about. I think what we got in here, series of beams. Again, you can see I have the same the box out on the top and on the bottom. You can hear so many labels in this one, right? So many labels in this one. So then you need to understand each and every one of them. The first one, you can see a cloud mark, this red cloud, 3.5 meters, that is the traffic lane. The purpose of bridge designing for traffic. So then the people, when we are driving, like on a bridge, we divide the lane, right? So that the people will drive within that specified area, not driving right in middle of the lane. So we got a lane width. In this bridge, in another area on the edge, you can see this a small element that is the barrier sticking out from the deck. That is the barrier. And then next to the barrier, you can see again, I have the mark. That's a shoulder width. You will learn this stuff later. There's a shoulder that is 3 meters. You got another 2 traffic lane. They are in 3.5. In the middle, you got another wide area left open. That is 5 meters. That is the median. Then altogether in this bridge, we got total width of the bridge 25 meters, right? Then we got a girders. How many girders? 1, 2, 3, 4, 5. We got a 12 girders in this bridge. And then they attach together by a deck. The width of the deck is 25 meters. And these bridges then supported on a, you can see a funny shape of trapezoidal shape of a concrete element, cross set. You can see that cross set and the bridge girder. I'm sorry, I didn't put an enlarged version of this one. There's a small box in there. That box you can see on the other end, we call the, as I mentioned before, elastomeric bearing. This bearing is support the bridge, the girder is supported on the bearing, and the bearing is sitting on the headstock. And in addition to that, you can see at the corners, the pipes are shown, a small rectangular element, that is the drainage pipe. Of course, in the bridge, when it's rain, you have to drain the water out. Some bridges, if you design in a way that the water will, like a flyover, for example, the one you got in Maradana, you can see you got a crown slope. The crown in the middle, and if there's any water, it will go all the way straight into the road. It's not that easy to capture as well, but still you can capture them. So this one, you got a drainage pipe to capture the water, one in the center as well, one in the center. In addition to that, the bridge is supported on headstock. Then headstock is supported by 2 piers, rectangular piers. Those piers supported by 5. You can see between the interface between the pile and the column, we have this the hatch area, or we call that one the cover protection, because we are building this bridge on a creek. We are providing a cover protection because to protect from the flood. So now in the bridge, like we discussed, you can see we got a girder. The girder is support everything on the bridge above it, deck, barriers. In addition to that, traffic lane and any other load on top of the bridge deck. Any question up to here? Is anything clear to you? Elena, is it clear? It's okay?
Yes, it's clear.
Okay, thank you. And then on the other side, I show you the arrows with the levels, the flood levels as well. Yeah, these are the information we're going to put in our bridge cross section. But for the time being, you need to see this one. This is the Super T. That's a girder type, a bridge. They are spaced evenly along the bridge deck. To support this 25-meter bridge, we have a 12 of them. The depth of this Super T is 1.5. If you look at the depth of the girder is 200, then the total depth of the bridge is 1.7 meter. Then again, I go to the similar cross section, but then you can see this one more clear than before, the previous one. You can see in our bridge barrier, we attach the lighting poles, and the other side, you can see we attach the sign structure. So your bridge deck, the bridge barrier, we need to attach so many other elements into that one we have to design. So we are designing a bridge in the sense, it's not designing a girder and the bridge deck. You need to understand there are so many other elements. We have to attach to that one. You have to design all of them. And then this is the same cross section, but I cut in a different location. At that location is at the end of the bridge, what we call the bridge abutment. In here, you can see this one. It's different. You don't have a column. You don't have a column. You can see this, the bottom, the straight line. That is the existing ground level. Now the bridge is quite come down to closer to the existing ground level. Because of that, we don't want column. We can just support this one on a horizontal beam or headstock, and then we can support that one on a pile. And then you can see around that bridge, because the bridge level and the ground level, still there is about 3 to 4 meter level difference in here. If you see this line, it's about 4 meters. Because of that, you have to protect around your bridge, as I described before. But beyond the bridge, you have a road that is just built on a fill. Behind the bridge, we just fill. Sorry, excuse me. We have to fill that 4 meter. Then we have to batter this one down. We're going to learn that one in here. Just to show you the different location of the bridge, you have a different cross sections. There are different forms as well. Then I put another bridge cross section. This is a quite common type of bridge we do in Asia. This is a typical Eiger Bridge. Yeah. This is typical Eiger Bridge we use for the 4-lane bridge. And then these Girders we place in 2.3 meter spacing. Again, we have a bridge deck on the top and the barriers attached to that. The picture on the bottom is similar bridge, but we use the steel beam instead of the pre-stressed concrete beam on the top. I think this one quite clear to you than the previous picture. This is one of the pre-stressed concrete Eiger Bridge. The reason I put that photos in here, the one is you can see the construction stage of this the bridge. This is quite common, I think, common construction in Asia. We normally cast the eye girders. Their length vary from 20 to 35 meter up to, and their space about 2.3 to 2.4 in general. And then we cast the deck on the top, and they were sitting on a crosshead and a pier. Yeah, we build the bridge. You can see this bridge construction involve so many activities, right? We had to build the pier, you had to build the headstock, you had to build the girder. Then you can see the way we has to construct the cantilever section of the slab. And you can see the bottom right-hand corner, this picture, you can see the red formwork is set up in between the girder. The amount of time you need to spend to build this bridge, I just put this one. Because the reason I put this slide in here, for you to understand, designing a bridge, selecting a bridge to use, it's not simple. The one reason is this particular expressway, I built before the construction. I was involved before I moved to Australia, 15 kilometers. Yeah, they use a very long expressway using similar kind of a construction, but it took so many years to build this one because you had to build so many elements in there, right? And then you can see the especially the next slide, the way we construct this headstock and piers and the part of the bridge already constructed. You can see on the bottom left-hand corner, we have a piece of planks putting on top of each other. You know the reason when we start constructing this bridge, there's a 15-kilometer long bridge, we noticed that one, this construction in here using this construction of the slab using this formwork is really difficult. It's time consuming. Then we go back and redesign the whole bridge with the plank. We replace the plank with the formwork, we replace with the plank, and then we design the whole the bridge as a composite section, right? Because this bridge we design as a composite, the I-girder and the slab. Then in addition to that, now we got another pre-stressed concrete plank. We got a pre-stressed concrete plank, and then we got I-girder, we got a bridge deck. There are three elements. We combine them together, we redesign. So the reason I put this slide in here, I try to explain to you, when you are designing and constructing a bridge, if it's a large scale project, sometimes the contractors may go and change their mind and they come up with different solution. They have reasons to do that one. Yeah, they have reasons to do that one. So when you are looking at that one, you need to look at both pros and cons and before you taking the decisions. That's what I put this slide. I spent a few minutes to explain this one. Another thing, this I-girder type of bridge is, yeah, you can use for even 10, 15, 20 kilometer expressways. The total length of this expressway, if I could remember, in Bangkok is close to 30 kilometers, but they build first 15 meters before, and they build the next 15 meters. We build after that. I could remember the numbers. We fabricated about 3,000 plus I-girders to build this one. It's got a many different forms and things. But we are talking about with superstructures and their behaviors, but I'm still talking about bridge construction in here. Anyway, that's very important. The other I-girder type bridge is the steel bridges. I think you have seen a couple of flyovers around in Sri Lanka as well. All these bridges actually I designed when I was in Bangkok. These pictures I put, the one on the top left-hand corner, you can see the bridge. It's better to be discussed about the top right-hand corner. You can see the shape of the width. You can see all this straight line go, 4 straight line go like a curve. And in addition to that, there are bridge beams, right? Then you can see cross frames you have. You can see frames around this bridge. They are bracings. And then you can see some vertical elements in there. They are studs. And then when you go to the top bottom left-hand corner, you can see on the same bridge, we put some concrete planks in there, right? Like I discussed before, this bridge also we design as a composite beam. The composite action now, the concrete to concrete, then concrete to steel. Yeah, you can design them. We did this one. I think this design has been validated long ago in US, in Texas A&M University. I remember I used to read the papers back then, before when we were designing this, when we were using this concept. In addition, the main advantage using this form of bridge is to you can prefabricate this one in a yard. You can bring them and you can erect. Another thing, if it is a steel, you can build with any form. You can say it's a curve girder bridge, curve girder width, the sharp curve girder bridge. I think this radius is close to 56 meters. I think we fabricate this, we lift this one on the side. So the construction efficiency is there. And you can see while you are building it, people are driving underneath. Yeah, you need the limited space to build these bridges. Now, you can see these bridges can get any sort of geometry. You can get the bridge to be to right shape. right? Again, you can increase your number of girders, you can increase the width of the bridge, right? And then when you are selecting a bridge to design, when you are selecting which form of material I need to use, what sort of bridge span we need to use, that is what we're going to work around today. I just give you these pictures because they, like, if you see them, these pictures only, you will see these are the elements in the bridge. You can see in this bridge, you have a bridge girders, you have a cross frame. Then you will have questions. Of course, you know the bridge girder will carry the load. Why we need to have a cross frame, right? Why we need to have a cross frame. We're going to discuss this one in bit later. The first couple of slides, what I explain it to you, you can build the bridge using the short spans, like 30 meter, 35 meter, 40 meter, maximum 50 meter, but not recommended. These bridges we build like a 30, 35 meter. It could be series of eye girders, or it could be series of steel girders. They have their own pros and cons. But if you use the steel girder bridges, they are very lightweight structures, and they will be their vibration on the bridge deck and things is severe than the concrete bridge, because concrete bridges are heavier and stiffer. And the next couple of slides, I'm going to show you another extreme in the bridge designs. Till then, we talk about the beam type of bridges, either super T or steel eye girder or pre-stressed concrete eye girders. And the next one, this is one of the bridge I work on as a box girder bridges. This bridge, the approach span in the elevation, the span length in average span length is 48.5 meters. We call viaduct. You can see the plan, it's got a really curvy shape. And that particular girder in this bridge, the same cross section, if I show it to you, we use this bridge, the width of the bridge, 27.6 meters, right? To beg your pardon with me, because I just want to go to step back to the one of the this typical cross section. In these eye girder bridges or steel girder bridges, our cantilever area of the bridge deck in order of 1.1 meter to maximum 1.2 meter. Yeah, maximum 1.2 meter. If you put beyond that one, the bridge will be vibrate. If I go to this cross section, what I'm talking now, this box girder bridge, the total width of the bridge is 27.6 meters. It's a one big unit. And the cantilever section of this bridge is 5.5 meters. Yeah. We call this one the twin cell box girders because I put only half of this section for you to understand. The depth of this bridge is 2.5. We're going to span 48.5 meters. It's a massive bridge, right? So before, what you try to build 13-meter wide bridge using series of eye girders, right? Those eye girders will carry the bridge load, distribute. Yeah, don't worry about the distribution. Let's say you have a 6 girders, you have a 3-lane, assume that 6 girders will carry 3 lanes. Now, in this bridge, we got a 6-lane, but it carried by single girder, right? Previously, your span of the bridge is 30 meters. Now this bridge, the length is 48.5 meters, right? You can imagine the way you jump from one end to the other end, right? You jump from one end to the other end. So sometimes people might argue because you got a one beam you put massive load in there, you increase the span, sometimes the construction cost in this bridge compared to the previous one may be increased by same pole. Not exactly same, but significantly large. Then when you are designing the bridge, you can go to these extreme ends. There is no harm is going to those extreme ends as long as there is a purpose of doing this one. There's a purpose of doing this one. For this particular bridge, you need to have this sort of structure. You will see in the next couple of slides. Then this bridge structure, you can see at the end, the depth is 220 millimeter. In here is 0.5 meter. And then this bridge internal distance between the web is about 6 meters. Then the distance between the center line of the girder to the end of the web is about 8 meters. It's significantly large. You can imagine the width of this, the web to web width is 16 meters because this is a half section I put. If you get to outer end is 16 meters, is equal to 4-lane bridge. Yeah. So it's really big. You can see these beams are really thin. I think when you are designing even the structure, 6 meter with 0.5 meter and then putting a traffic in here with that cantilever, you're going to wonder how this thing is going to work. But yeah, it's designed, it's built, and it's working. And then this is the one extreme end of the cross section you can go. You can go in between. This is one of the largest bridge, 27.6. 6-lane bridge is largest. Now people go up to 8-lane, even 10-lane with this one, different multi-cell kind of a box girder bridges. The depth of the bridge is 2.5. I'm not going to give you the numbers, how to get this, how to get L over 20, L over 30, L over 22.5. The reason I'm not going to do that one, if you design the bridge to a different standard, the loading on the bridge, they are different. The lie load on the bridge, if you use the Australian standards in one end, if you use the Astro is in the other end. So when you are designing the bridges to a different standard, yeah, so these member thicknesses won't work. Yeah, you can't just copy this one and to use in then another standard. Please remember that one. But you can use this form. You can use this form. The example I want to give you, you can be in these ends. You can be in the girder spacing. You can put even 1.8, 2.4, 2.4 in average, but we design bridges up to 1.8 meter spacing in a girder, right? The span of the slab is 1.8 meter go against 27.6 meters. It's got a about 6 meter cantilever, and then you got a 2 beam in between. It's more than 7 meters. Yeah, you can go to these extreme ends because when you put this loading, all this thing will be bend and behave. We're going to learn this thing in later. Any questions up to now, please? I need your feedback because the at least do you all understand what I'm trying to achieve and talk? Or? All right.
Yes, sir, we understand. And I don't see any questions in the chat as well. You can.
Okay, thank you. Thank you so much. And this is the cross section of this bridge, right? If I go to this, elevation in here, this bridge is 600. This approach span is 670 meters. We have this bridge, I think, close to 200 to 300 meters space. I forgot the number exactly, expansion joint. And this bridge, 48.5 meters, 27.6 meters, but it's designed with a single column with the footing and single row of pile. Single row of pile. Single row of pile. Okay. Then sometimes people might say, oh, no, this bridge is not safe for me to drive. This bridge is not safe for me to drive. Why this designer put 2 meter diameter single row of pile instead of why didn't he put, you can calculate the area, right? Why didn't he put 4 piles like our table? That is one of the most stable element you have in your house as a furniture, right? You can jump, you can sleep, you can do anything, right? It's never going to collapse. You put the 4 piles. Why can't we build that pile? Why we have a 2 meter diameter pile? You can see the pile capacity 30,000 kilonewton or 30 meganewton. It's a massive pile. The length of this pile is 60 plus meters. Why do we do that? And you got a column 6 meters in width, but if you look at the thickness of this column, if I could remember these numbers, I think it's about a meter, right? It's a meter. Then if you look at into the page in the longitudinal direction of the bridge, in the longitudinal direction of the bridge, this structure is slender. If you look at the total height of this bridge, the bottom of the toe, pile toe level to the top of the bridge, this is 60. This is 2.5, 62.5. This height is about 10, 72.5. This height 2.5, 75 meters. This is in clay. If I go back to this picture again in here. So when you are on a bridge, you driving a cars, you put vehicles and you brake, you stop your vehicle, then you accelerate, you get a traction and braking, creep, shrinkage and doing everything. Then this bridge all the time pulling in and out, right? Thermal behaviors, this bridge is moving. It's moving like a cantilever structure. If you bridge, if you design as a 4 legs in here, this bridge foundation will be acting like a table. As I mentioned, you can go and sit any place, you can go stand in there, right? And then it's stable, right? It's rigid. Then you can achieve the flexibility of the foundation. Because this is, is in a clay, in the clay area, you get a significant flexibility from your foundation. When you make your bridge substructure or the column flexible, then you can let your structure to deflect more. When there is a creep shrinkage forces in here, because this bridge we build like a monolithic structure, you will see this one detail in later, all the forces apply on the bridge, right? It's not going to translate into the structures because part of that will be translate into a deformation. This is the one principle they employ and design this bridge. Yeah, because that is what I just want to explain it to you. When you look at the bridge design, don't make judgment straight away. Don't make judgment straight away. Give a lot of thought and spend the time. Do your own bit and then see what is the principle this particular designer employ to design this bridge. That is the whole purpose of this slide, right? Because now, for example, if you use like a software like a Midas, it's quite easy for you to model this thing and getting load and forces and things designing. It's not that difficult, but the philosophy behind this one, the formation of this bridge, right? The main purpose of this bridge to transform all the traffic load into the foundation, into the ground, but in the same time, get the to reduce the number of expansion joint. That is one of the main reason we try to come up with the solution, because the expansion joint is one of the worst thing on a bridge structure. You need to have them. I think you all have experience driving along especially flyover bridges. Every 25-meter span you got to join. You can hear a bang, 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 bang all the time, right? Even the road authorities, they have a headache as well. Yeah, their design life is 30 years, but you have to replace them before even 15 years, because it's very difficult to manage. Even it's really inconvenient for road users as well. These design solutions came to optimize the design as well as to get the better outcome, right? It's using not only the whole environment, especially the ground condition. You trust me, you can't do the same thing if you have a shallow rock like 5 meters below, someplace we found in Sydney, like a sandstone. You can't just do this solution. Then you need to find a different bridge solution. If your foundation is really stiff, then if you try to push the creep shrinkage forces, this area will be cracked at that interface. So different solutions we come up in the bridge structures according to their behavior. We need to have we need to give extra thought into that one. Yeah. Any questions? This is in the same bridge. We have a different structures. We put it in here. Still, you can see the pile is still big. We have to put a portal frame. You can see on the bottom in the screen, there's another cross section. There's another bridge in here. Yeah, we are putting this this bridge we build next to an existing bridge, exactly same as what you are having in Colombo at the moment across the Kalini River. There's an existing bridge next to that one. There was a Exodus bridge is already built, similar to that one. Yeah, and they build next to each other, but in some places is crossing. Yeah, and then we need to have a portal frame to get the bridge across this one. This is something I put in this one in here, the construction of the bridge. This is the column construction. You can see it's architecturally pleasing. You can see people standing here, reinforcement. You can see these pipes. These are drainage pipes, right? It's a closed cell box. When you collect the water here, you can't let to go along the bridge. So what you need to do, you have to collect the water in here. They didn't have a drainage detail here. We collect the water at the middle web, and then we get that one to the column, and then connect this one to come out from the column at the top of the put-in level, and then connect it to the drainage pit outside. Another thing I just want to explain it to you, this construction of this bridge, you can't use the scaffolding or form, but we use for the first two span in the back in there where the span is low. We use the gantry, this bridge building gantry. This gantry weight is 1,800 tons. Yeah, and it will be acting like us. Like I'm standing in here. If you see this picture in here, it's like this. Yeah. During the construction of the bridge, this gantry acting like here. After the bridge construction, the concrete cast, we do the post tension and everything. We lift the gantry like that. You can see this arm. It's hydraulically we move. It's not a rocket science. It's just the way you hold your hand together and open up. That's the same thing we employ in here. It's your hand. This is a piece of your hand. Is open up in here, and then make sure it's open up and push. It will move across. The principle we use in this moving across is like a seesaw. There's a point, I don't have that picture. I couldn't find today. Is exactly come to the one point. The center of gravity come to the center bogie here, and then the end of this gantry, it will rotate and will reach to the bogie in the front girder. You can see in this bridge original plan and elevation. It's a very nice piece of line. When the designers design it, they are straight bridge, they are continuous span bridge, maybe 400 meters in length, for example, expansion joint to expansion joint. But when you are building it, you build your column, of course, no problem, but you build your column, the section of the bridge, section of the box girder or the superstructure, monolithic with the column, and then you build the rest in between. You build the rest in between. And if you look at in terms of the loading, we all know when you have a concrete, it creep and shrink. So then all this timing and edges will affect your design, because in your bridge, if you looked at during construction, after even you finish, you have a different edges. Each and every element in bridge, it has a different edge. So then the creep and shrinkage on the bridge have a different strain level or else different forces. So that means it's time dependent. Forces will be vary all the time. That is one thing you need to take that one in mind. But please remember that, because the designers cannot predict the way it's going to construct, how many days it's going to rain, how many accident is going to happen in here. You need to make your own assumptions and you need to do your designs. And then the contractors, they are building a specialist contractors. They're going to go back and reanalyze this bridge, and then they will present when you are building this one, it's going to meet the designer's intent. Therefore, what I try to explain in this slide, when you are designing a bridge, when you are building it, right, your structural element behavior, the final form is one way, the construction form is another way. I really miss one thing in this Eiger construction, because the Eigers we first lift and we cast the deck. After it's concrete hardened, it's becoming a composite section. I think each and every one of you know the composite construction, and yeah, that one become the composite section. The behavior will be different. And this bridge, there is no this bridge also got a composite construction actually, because we build the bottom part of the two bottom web and the two webs. Then after that, we build the top part. Yeah, because the reason is the constructability issues. I'm not sure whether I have a pictures in here or not. No, I don't have it. Yeah, this is the construction of the approach viaduct. Because then in the approach viaduct, then it's reached to the river. The river span is 229. The approach spans of this, the 130 meters, the total length in this bridge, 489. I'm really proud to say I involved in this bridge. This bridge is the second, the largest span in the world at the moment. The largest one is in Norway, but it's a small 2-lane bridge designed by the same company. Its span is 301, but if you get in the size and extent, I think the largest one is in Brisbane, Gateway Bridge. The span is 300 meters or 290. I forgot the number. This is 229. Yeah. This bridge, when you are building it, it's not going to easy as well. So we had to build this one across. You can see in the middle of this bridge, there is a 60-meter width. Sorry, I didn't put that number. There is a clearance. This 60-meter width and this clearance we need for navigational requirement, because this bridge, Chayophraya River, they use a lot of boats. They use the boat to transport things. Because of that, you need that clearance requirement. That is the one reason you can put the piers in the column as well, and other in the river conditions as well, because it's not easy to build a bridge in a river. And this bridge, 489 meters you have to build. If I just give you a simple number in terms of the construction cost, when you build a Eiger Bridge, if you said, say you spend $5 million per meter length, right? Not 5 million. I will say the, yeah. If you said X amount in that one, then you have to spend about 20, 30 times that value to build the same bridge. Yeah. But we have a purpose to do that. Sometimes you have to do. Then what are the elements involved in this bridge construction? There's a massive girder in here. If you can't see this one, the depth of this is 12.5. The width is 27.6. If I go back to elevation, when this come to middle, the depth is only 2.5. 12.5 is reduced to 2.5. So this bridge, the pile length is again 2 meter diameter pile, 30 meganewton. We got a 25 pile, elliptical footings. They are 25 meters and 21 meter, 25 in length, the 25 meter width. And we have a very strange, very the architecturally pleasing columns and thing. This is the construction stage of this one. You are designing in this bridge, you get the load, you put everything in there, you build this bridge, but the construction staging play a massive role when you are building this bridge. You can see these piles. It's a 2 meter diameter pile, the 3 meters in length. I could remember the one end of the piers we have on the east and west. The one end, the river bed is about 17 to 18 meters below. The other one is a bit shallower than that. And for us to build, another thing, the water level fluctuate in the river. This is from outfall is about 40 plus kilometers in upstream, but still the water level change in the river significantly in the evening. This you can see the people are standing in here doing the welding, but after 2, 3 p.m. later, they can't work anymore. They can't do any welding because this whole area is going to flood. And then we came up with the design solutions to build this bridge. The height of this footing is 14.5. You can't cast the 4.5. You can't cast this footing in a one go. So you have to cast that one in a different stages, and to make sure that the heat hydration is not going to make a lot of cracks. So in addition to that, this one got a lot of pre-tensions inside. And these are massive mega structures you're going to build. Sometime I think if you design building, maybe you may have a similar kind of a footing for your massive high rises, and then it's very big, and the construction cost is really big. That is what I want to tell you. The reason I put this one, you are in two extreme end. If you are designing and building a flyover, it's one end. If you are designing and building the bridge across the river for a purpose, because this one we need to have a navigational clearances, and the river bed is really deep. It's not easy for you to go and build a bridge in the middle of the river. That's really difficult. You have to build a lot of copper dam access structures, because you need to bring heavy machineries. And because of that, there are so many reasons for you to come up with that solution. Don't look at in paper and comment on that one. Yeah. The designers to come up with this solution, they have their own reasons. If someone else come up with a different solution, yeah, you can have a look at that. But you can say the design team A came up with this solution, design team B came up with this solution. You can't argue design team A is the best, design team B is not good. No, you can't do that, because they have their own reason to come up with the solution. Sometimes if you get at the end of the day, these two curves go up and down, at the end merge to the same point most of the time. If both are really good design teams, their solution may be different, but end goal is the same. But if you look at in terms of cost and other thing, more or less the same. In the bridge designs and the superstructures you have all these extreme men. You can see this nice picture. when they were finished, this the column head section, and this is on the right bottom corner is in here while they were building the pier head, and the top right hand corner, this is when they were assembling the bridge builder or foam traveler. You have different name. I could remember this one. This got about 100 ton, the total weight. There are so many pieces assembled together. We formed this one. Yeah. And you can see on the top left hand corner of this, you can see the construction of this bridge. This bridge builders is constructing. I want to tell one thing. People may not agree or disagree with me, because with my own experience constructing this bridge, things we encounter. If you build a balanced cantilever bridge, we call this one balanced cantilever bridge. It's like you are building both sides together. But this bridge, we have a very special construction way. We call asymmetric construction. Because if you build a balanced cantilever bridge, I will tell you, because this side of the bridge and the other side of the bridge, you have to build in the same time. So you need to have one crew here, another crew there. If you have a 4 segment, you need to have 4 different crews to build this. Then you need to have 4 bridge builders to do this one as well. You can have 4 bridge builders, but the construction time, the amount of the labor you need to put is more. Another thing, especially the people, those who operate this one, there are a handful around the world, not many. So the way we build, we make asymmetric. We came up with, we changed the original design. We came up with the asymmetric design because the one segment go ahead front of the other. Because of that, you go further away, you have a massive piece of 100 ton plus weight of this segment is providing unbalanced movement in this bridge foundation. So you have to check that one. You need to design that one. In that way, we make the construction efficiency, because these are the things you can come up with when you are building things. But when you design in this bridge, you don't want to do those assessments. The reason why I said these are the bridge have a significant capacity. Why? Because, you know, when you are designing a cantilever beam, anybody can design cantilever beam. That's what we learn in our second year. When you are designing a cantilever beam, so your tension is on the top. So in these bridges, you just keep putting. You have to keep adding the pre-stress, because you can't design reinforced concrete. Pre-stress on the top. You need to have a significant amount of pre-stress, because your maximum bending moment in that interface on this bottom left-hand corner that you can see, in that interface, you get the maximum hogging moment. So your maximum pre-stress is in here, right? But you keep doing it until you come and stitch these two together. Another story in here, these bridges, because you know the cantilever element, the deflection is PL cube over 3EI, right? So when your L is larger, just keep going down. So when you are building a bridge, we have to camber out, because you can't have a road surface go up and down like when you are driving a car. So you have to build your bridge up like that. So this calculation and getting, we call the Camber diagram, this calculation people predict is all theoretical. You build your bridge like that, assuming this goes like this. You build in here, you set, and because you build this bridge and finish, and you coming, you can see this one is go close to the middle, but this one coming slow. When you are coming here, this one already finished. The other one then come here. You are lucky if these two are together like that. But sometimes they are not. If I use my, like this, the two bridges, the 1 and 2, they are not in the same location. Yeah. This bridge is one of the major problems when we have what we call in the middle, we have a reinforced concrete cast in situ section. We call stitch 4. That stitch 4, you have the gap like this. You can't build your bridge like a 20, 30 acceptable, not like 100 mm or 80 millimeter or 100 millimeter cap in here. Yeah. And then the to set that bridge element together next one is not that easy. We know from our experience, yeah, we had those situations, we rectify them. And the reason I said these bridges have a massive capacity, I could remember the amount of the loads we put, and we do our calculation. You can have 100 ton. This girder itself, if you get 100-ton crane in here, it will deflect like that, but they never work that way. They never work that way. Yeah, and these bridges, we are designing as a cantilever. When it's linked together, this bridge will be acting like a one end simply supported because the other approach span, and the orders is connected with the approach bridge. It can be continuous as well. And you got your pier headstock here is continuous, and continuous here is a continuous span bridge, but you construct them as a cantilever structure. You know, your three span, the cantilever, the three span continuous span bridge, when you place the load in, the variation in the bending, because what are the additional loading when you pour the stitch pour in this balance cantilever bridge, what you're going to get is your traffic load and the barrier load and other loads. Yeah. So therefore, this bridge design and construction and the if you get the behavior, they are very different. What I try to explain up to now, when you are designing a bridge, right? It's not you are running a computer model and just calculate the bending, develop the bending moment diagram, then all the bridge, if it is not steel, if it is reinforced concrete one, we use the pre-stress and post-tension, you design them, you design your reinforcement and leave it there. Don't think that you did your job. You have to sit back and see how, when we are going to build this one, how it's going to behave, right? So then if it is behave totally different to the way I'm going to design it, you have to go step back and you need to look at that one as well. Yeah. This is another thing, like if you are the road agency, you need to do the same way. You need to look at this bridge, design one way, building in another way. Then who is going to fill the gap? Is you or contractor or designer? Or you need to be really mindful, because that is why I put as an example these two extreme ends for you to explain. Yeah, I think you might tell me, Rohita, you spend nearly 1.5 hours close to our time. You haven't discussed anything about superstructure or substructure behavior. Am I correct? Can someone say yes or no at least? Yeah. But I explain it to you, bridge structure behavior, because we all structural engineers. I'm not going to tell you that if you put the beam, you know, the load you are going to get is, if it is a simply supported, you're going to get bending, shear, and torsion. Yeah, each and every one of you know how to design them, right? How to get them, we learn later. But how to work them around in a bridge is not simple or straightforward. Yeah, every time spend some time, draw sketches and think, and then every time the people with experience have a discussion, I think they can give you a lot of things, because the bridge design is always, you are in extreme end. Sometimes you have to work on a middle path as well. You will see later on these presentations. This is another type of bridge. Again, we use not, I don't think this is economical at all in Sri Lanka. The reason what I'm putting this bridge is we call voided slab bridge. It's the piece of concrete segment. Yeah, it's a box girder, but it's not like a box girder you see over there. This bridge is not that wide as that one, but it's still 19 meters wide. And this bridge, we to reduce the weight of the concrete, we have these holes, and in the same way, this whole the hollow sections we put inside like a duct, air conditioning duct, if I say, and then this the gaps between the ducts is going to be acting like the webs. And you can see I marked this one in this, the marked in here. You can in this particular bridge, we have a 4-meter section that's we're going to use as a shared path. Shared path in the sense people can walk and people can ride bicycles and things. It's dual purpose. In addition to that, on the bottom, you can see you got a conduits. We put conduits in the walkway because you need to get the electrical, water, and so many things. Because in here the thickness of the concrete is large enough for you to provide conduits for services. In addition to that one, you can see there is a curb as well in this bridge, because the people can't walk in the same level the way you ride. Because of that, we have the curb, and we raise that one. It's about 200 mm, and then we have the walkway on the top. These are not that long as a span bridge. This not in the heavy speed environment. It's a 60 kilometer environment. This is about 40-meter length. If you look at the video the video I put in my previous, I couldn't play that one on that day. I'm really sorry about it. But if you play yourself while you are later on with that link, you will see this bridge called it's connecting to roundabouts. A Kangaroo Valley bridge is 40 meters in length, 60 kilometers per hour. Because of that, it's quite safe for people to walk in here. You can see, in addition to that bridge, we got the barrier. You can see this very funny shape steel element that throws screens. And the other elements, we saw so many things in the bridge. In the bridge, we have not only the bridge deck, bridge beam. The beam may be an eye girder or kind of a box girder, significantly large size. In addition to that, you have a shared path. You got a noise pole attached to bridge barrier. You got a lighting pole attached to bridge barrier. We talk about you need to have a drainage, especially if it is a flyover bridge, it's okay. But if it is the viaduct or elevated expressways or something, a long bridge, still you need to drain out the water. In addition to that, for the bridge deck, we're going to attach expansion joint. You can see they're going to attach to the bridge deck. Yeah, the throw screen we need to attach, because sometimes when you build the bridge on the face, the people put up their advertising board as well. Yeah, advertising boards as well. So these are the elements we're going to attach to bridge, in addition to the main element in the bridge. Main elements in the bridge is the bridge girders, bridge deck, and the bridge barriers. These are the three main elements in the bridge, but the rest, all these other elements, they are part of the bridge element we need for the functionality requirement. We need all these small elements in there, but in terms of the bridge design, the main thing you are designing is these three elements. The rest is assembling. They are the miscellaneous structures you're going to design. And then when you go to the end of the bridge, we call the bridge abutment. That is where bridge is interfacing with the road, because you saw in the previous one, the level difference is around 3 to 4 meters. Then you can't simply assemble them together, and the bridge is very rigid, and then the ground is really flexible. Then I can give you one example, my experience in Bangkok. The bridge we designed, the settlement in the bridge is about order of about 20 mm. But in the ground, in the soil over there, when you build, settlement is about 200 mm. So you got this red point in here. Over here, your settlement you expect is only 20. If you expect your settlement back in here 200, so geotechnical engineers is come up with very nice solutions. build another bridge behind that one. It's about another 70 meters in length to absorb that settlement. Yeah, there are different, they use the bridge with the, allow the bridge to settle gradually, or else they build the bearing units and let that one to settle, then the soil to settle, but it's gradually. When you are designing a bridge, that settlement interfacing you have to do, that's all depend on the ground conditions. So when you are in a good ground, your approach bridge is a very standard. This one in Australia, most of the places we use is 6 meters. And you can see we have a batter around because this level difference, your road surfaces, unless otherwise, if you have a space, you can batter that one. The batter is 2 to 1. That means if your bridge is 4 meter, level difference is 4 meter, then your batter, you need to have another additional 2 to 1 batter, mean 4 meter height. The horizontal dimension you need 8 meters. If you have that much of land, if you don't have a land, for example, if you build in Colombo, land like a goal, so you can't batter them, then you will build retaining wall all the way through, like we saw them in the first presentation, like RSWs. And then at the other one, the access stairs, you need the access stairs because in a bridge, like last session I explained it to you, bridges we designed for 100 plus years, and but the bearing won't last that one. Their design life is maximum about, they expected 35, but it will last about 40. It's depend on the way the bridge articulation, you will learn later. And then to inspect them, and sometimes when the bridge behavior, settlement and other thing, unexpected thing happen in the bridge, and then the bridge will, we call the walk, the bearing will walk, and then you need to go and readjust the bearing, or else you have to replace. For that, the maintenance crew need to access these places, so you need to provide the access stairs and the walkways underneath to go and access them. Yeah. In addition to that, if you are building a bridge in a flood-prone areas, you have to protect them from covering as well. Yeah, there are so many elements attached to that one. This is not you designing your girder and the deck. No, it's a lot of elements you need to interface. Not only the geometrically, in addition to that, the ground behavior as well, you need to take into account. Yeah, this is one of the typical cross section in the abutment. The bridge abutment. The bridge abutment, we got a headstock where it's going to support the girder in the back, because there is a level difference. That level difference is equal to the total depth of the bridge structure times the thickness of the bearing. In this one, we have normally a wall in the back. We call curtain wall. Back of the curtain wall, we're going to backfill, right? We're going to backfill. And we're going to backfill to make sure that this ground is good. In addition to that, because behind the bridge deck, that's soil, because you can have a water infiltration. To drain the water, we always have a drainage blanket behind the abutments. The abutment, doing a different purpose. Abutment is linking the bridge and the road behind together. In the same time, it's hold the surrounding as well. And you will see this is the cross section in the abutment. Around the abutment, we normally put what we call the wing wall to hold the soil in that area. The one reason you need to remember this one, the wing wall you need for many different reasons in the bridge. The one thing you can see, when you get the traffic load around in here, that the soil pressure and distribution, unless otherwise you have a sufficient space to batter that one. If you build something in a area, you can shorten this wing wall. Otherwise, you need to have a wing wall to hold this the soil around here, because otherwise, with the loads, with the deformation in the structures, this area of the bridge in the approach section won't last the intended design life. These are the different form of wing wall and the abutment substructures. And this is one for the segmental box girder one. and it's the same one, the box girder we use. We have a similar wing walls, abutment structures, and this abutment structure RSW1. Yeah, this is the around the abutment structure that we provide the cover protection. This is one picture. This is the cover protection. You can see quite an old bridge. It's provided in the river and the abutment area. Any question up to now? Any question? Okay, I will ask you a question. Yeah. Huh? Okay. No questions, right? All right. The load transfer mechanism in the bridge. This is, I thought a lot because this presentation is before when I start developing this one, a lot of things came to my mind how I'm going to present this one in different way, but that's I thought the current way, the best way to talk about the beam. You've got a torsion bending, and because we're going to discuss that one later, but I'm going to talk to you about two extreme and Eiger bridges against the box girder bridges in 2N. In terms of the construction and the cost wise, they are in 2N as well. But in terms of when we're going to use them, they're going to do the same purpose because we're going to build them for people to ride. All right, this one in here, load transfer in a beam slab bridge. Yeah, I think you saw this skeleton and the first this diagram. We got a wheel load in here. That is the weight of the truck. When you put that wheel load, because in the bridge you got the dead load. That is the weight of the girder, right? All these bracings and the deck, barriers, asphalt. If you have a use of shared path, though additional concrete toppings, and then if you need to put lightings, all those where if you need to have more barriers, the edge barriers and median barriers, all those weights we have in the bridge. In addition to that, the traffic load. Together with the other load, you can't see them like creep, shrinkage, thermal expansion, contraction, earthquake, flood loading, you name it. There are so many loads apply on the bridge. But for the bridge deck mainly, dead load, we call superimposed dead load. We call that one superimposed dead load. The reason is we put that load after bridge deck is hardened. Then if you design this element as a composite sections, then whatever the load you're going to put on the deck after the concrete gain the proper strength, this deck will be acting like a not individual beam. It will acting like a composite section. It's got a more strength, and that composite section will carry the load. The ST, superimposed dead load. For example, barrier. Well, we can't build the barrier before you build the deck, right? And asphalt and this lighting, they are permanent load because they're not going to change. And then those loads, superimposed dead load, then the traffic load. These are the load on the bridge. When you apply this load on your bridge deck, from the deck, it will goes to the girder. From the deck, it will goes to the girder. From the girder, I said before, between the bridge superstructure and substructure, the link is the bearing. It goes to the bearing. Bearing will carry the vertical load. Bridge is, because of the loading, is flex, it move. Bearing will allow bridge to do that one as well, like we do our hands like this. Yeah, bearing will allow to do that, all that work. And then from the bearing, it goes to the headstock in this, I'm talking about the beam slab type structure. It's got a girder, it's got a bearing, it's got a headstock, the horizontal member. Then from the headstock, it goes to the column. From the column, it goes to the footing. From the footing, it goes to the pile. From the pile, it goes to the soil. This is the standard way of the load path of a bridge, right? why did I put this particular slide in here? The later on you can see this load path. From different bridge form, we can come up with different the same load path, but different element combining together. You will see in next couple of slides. The reason I put this one in here, one thing when you are designing a bridge, you have to design the deck, you have to design girder or bearing or headstock column, no way putting pile, soil interaction. Oh my God, so many things. Why can't we do this one with easy way, different way? So when you are building this one, okay, we go opposite: build pile, build footing, build column, headstock, put bearing, because you can't put your girder without bearing, but we do basically, and we have to jack the bridge. Sometimes they do, and girder, deck, all the barriers and things. You see, it's go opposite direction. It's like exact same way you design a building, right? And top down and bottom up. So now in this element, when you design and build and hand over to the road authorities, what's going to happen? They have to maintain them. They have to maintain them. So each and every element, they need to look after them. Then more the element, more problems, right? So because of that, this is the slab and beam and slab type bridges. You have all these elements. You can't avoid them, right? You can't avoid them, but later on the slides you will see it's not recommended, right? When you go to next slide, I'm going to a box girder. It's a box girder bridge. It's not the box you saw in this previous project, because in that box and this one is a bit different. This box, you can see a girder and a deck is all of one unit. It's a box section. We combine girder and the deck together. We create the box section. So we have now only one unit. It's good. And then there is no headstock in here because this girder directly supported on bearing, but bearing directly sit on column. So you combine column and headstock together. Then you remove box section, you remove the girder, sorry, you remove the deck and the headstock construction. Yeah. So remember that Eiger Bridge construction, I show you what a trouble they took to build that deck, right? You saw that the cantilever formwork system, and the one I mentioned to you, that bottom formwork system we used before, it's not working, slow. We changed the whole bridge design. We put the plank, replace with them permanent planks, and then we designed the bridge. When you using this kind of a bridge, you can see you don't have that problem because this segmental box girder bridge, we prefabricated these elements in the yard. We bring them together. It's like a jigsaw. We place them together, assemble together, post tension in the side. You can easily build. The building pile, in this particular one, we combine the put-in and pile together, like not like in the previous example. This one, the column is directly sitting on the pile. We eliminate many things in here. In terms of the construction cost and the material and everything, this solution is better, right? In terms of maintenance, less element, less maintenance is better. Now you will ask me a question. So why they'll on earth, every bridge on earth, why don't we use the same solution, optimize that one, and then we use that one, right? Yeah, that's, you can ask me why people are having different form of bridge. Why can't we build one bridge? Like, yeah, like we using internet. Yeah. But it's different. The cost factors is different. You can see this construction of this bridge, this monster gantries on the top. Yeah. If I give you just a little numbers, The assembly take about 6 months. You assemble that one, to dismantle that one, at least 4 to 5 months. So it's close to 1 year. So when you're constructing this bridge, you have to spend almost a year to assemble this and dismantle that one. But this bridge construction is very effective if you build not like a 300-400 meter long bridge, but you build 300-400 meter long bridge, many of them in the same project. But sometimes people think it's cost effective, but if you're building bridges, they are quite long, like a couple of kilometers, then this bridge construction is very effective. In terms of the maintenance and the value for money, especially for the road authorities, these bridges give a better solutions because the less bearing, less expansion joint, less maintenance. Yeah, and yeah. So these bridge solutions are ideal, but their initial costs are much higher. Because sometimes when you do bridge construction, I think especially the road authorities, in the planning stage, I think they do the balancing out what is the present worth value, the present investment and the maintenance cost and the decommissioning cost, and then what is the overall cost and all this, the financial modeling they do, and they decide which way to go. But still, this is quite common. To design and build this bridge, the American Segmental Bridge Institute, you can see this one. I don't know whether you can see this. Can you? Can you see this book? Can anyone see this book I'm showing to you?
No,
No, so
not
we
very
can't see
clear,
the
sir.
book.
Is it
remove
now?
background
No.
stream, then we can see.
Okay, no worries. I think this book, I think I will share with a copy of this book. I think that's why I not put many numbers and thing. There are so many information available in that one. You can build, you can design. This will give you all the valuable input, what you need to know about designing like basic numbers, basic information to design this kind of a bridge. The reason is the load transfer mechanism. The box, like we saw here, it carry all the load. The box carry all the load, straight away send it to the column, so through the bearing to the column, then to the pile. Especially these bridges, again, the Bangkok is clay, use the flexibility of the ground. The one thing I forgot to mention you before, you had to be very friendly with your geotechnical friends. Yeah, you need their support you need their input when you are making these decisions. And then the bridge I discussed before, continuous span post-tension bridges. You can see the box, girders and deck combined together, we form a box. Now, there is no bearing in this bridge. You can see no bearing. And the column, there is no headstock, there is no bearing because the column and the girder is monolithic. Now you can see from this picture, this width is 6, how thin the thickness of this member, so to get that flexibility. So we combine them together, we have a column. In this particular one, we got the footings. Because of the thickness of the column is not large enough to put 2 meter diameter piles, so you need to have a larger and enlarged area. That's we need footing and then to the soil. Yeah, you can see now in this bridge is much better. But initial investment you had to place in this bridge is significantly large because the construction cost, I'm not sure around the world how they're going to use a different way, but all the construction, all this additional costs incurred in this from the contractors, they estimate what is the cubic meters of concrete. That's how they pricing. But in the payments term, they might say pile cost this much, column cost this much, footing cost this much, girder cost this much. Yeah, there are different arrangements, but when they were costing it, they put all this, the additional formwork system, all those things in their overhead. Yeah. This is another, this bridge you can see in my background, the one on the bottom left-hand corner, Industrial Ring Road project. It's a very interesting bridge. The pile is 1.5 meter diameter. The length is about, in this river, close to river, is about 70 meters. The interchange height is about 50 meters. The length of the span between these two small elements, this girder, the span of the bridge is 66 meters. The slips roads connecting the other side of the approach viaduct and the cable stay bridges. The slip road, the longest one, got about 600 meters. It's all continuous from one end to another end. You will see this one again in the bridge articulation. And then the bridge flexibility, they use this one. I could remember this one. Still, I could remember when we look at the design calculations. In this particular bridge, there is no code to get the slenderness ratio. In this bridge, if you calculate the slenderness ratio based on the design code is exceed, because they have that much of flexibility in this bridge. Yeah. And the beauty of this one, when you build this bridge, yeah, it's maintenance free, almost free. Yeah. If you properly detail it, if you consider the durability design to depth, these bridges will last definitely more than 100 years without any problem. Any questions up to here? You can see.
May I ask a question?
Yeah.
I'm Dilina here.
Yeah.
I was wondering, almost all the columns are very thin in one direction. I mean, in the longer span direction, it's very thin. What is the reason for that? Usually in buildings, we put the thicker section in the direction of the span. But in the bridge columns, we can see almost all the time the thicker side is on the other way.
Yeah, because of these bridges, we need the flexibility of the bridge, because you will see in the articulation, we need the flexibility of the bridge, because this bridge, you can see the length of the bridge 660. The bridge is subjected to creep and shrinkage and thermal expansion and contraction. As a massive force, they are in a spiral curve. That load need to absorb. So this structure is continuous from one end to another end. So that flexibility in the bridge will allow that force will translate into form of deformation. Yeah, we allow bridge to deform. And the way we articulate that one, I will explain it later in my slide. So it's because when you design the building is different, because you know exactly your direction of the maximum, the bending, and which one is the major axis and minor axis. But in here, the flexibility will help, because that force, that axial is along the bridge longitudinal direction. So because of that, we need to have that flexibility to get the bridge. In the other way, we widen this deck as much as possible, and to get this, you can see if I explained that bottom width of this girder is 16 meters, and then to get this the bottom flange area, the force transfer and other thing. Yeah. Did I answer?
Yeah.
Answer your questions? Yeah. And these are in the continuous span post tension bridges. You can see you have only deck, and then you have only pile. You can have footing. Because of that, these bridges will have a expansion joint and bearing, but there are very few numbers at the 400, 300 plus meters span. So the maintenance cost is minimum. If you really detail and design these bridges, they will last more than 100 years very easily. But initial investment is very high. Big construction cost is very expensive. I'm not supposed to give the numbers, but that 15 kilometer one and this one, the level, this is less than 1.2 kilometer. That bridge costs, and at 15 kilometer expressway, it's got so many things. And this bridge, it's just different by about 20-30%. The cost of these bridges are very expensive. Yeah. And the performance wise, it served the purpose. Then I'm going to share with you something very different. I thought, gave a lot of thoughts, and I thought, if you are a bridge designer, you should know what we are doing. I'm talking about bridge barrier. I'll spend a few minutes on that one. Okay, why do we need bridge barriers here? Right? We need bridge barriers to contain the vehicle. It's quite obvious, right? Everyone in here agree with me, you need bridge barriers. You can see one on the first hit the barrier, but still you can see his tail split into two pieces. It's there. The other one, yeah, halfway fell down. The other one you can see it's broken into two pieces. Another one, unfortunately, it's the broken, and then maybe a lot of people die. You can see these pictures. If you look at all these pictures, you have a highway underneath, right? When you are driving on the top, you are crossing the other lane. So if your vehicle, like this kind of a truck, it fell down onto the highway in the bottom, you can see how many people is going to lose their life, not only the person who drive this one, right? Because of that, the purpose of the bridge to create a safe environment for our people, and because then we need to have a safe environment. And you can see the barrier design in the bridge is very important, one of the very important thing. So then first question is, why do we need barriers? Of course, contain vehicles, it's quite obvious from these pictures, right? So then, should design with sufficient strength. Of course, if you not design, this is the outcome on the bottom left-hand corner, right? One in the middle, this is a one cross section, the bridge barrier. I don't know whether you can see that one, sticking up from the bridge deck, and it's rigidly connected. So when we are connected rigidly this one, then we should design rigidly connected to the bridge deck, should design with sufficient strength to transfer this impact load, at least to contain. It doesn't matter it turn around, but in oncoming traffic in here, sometimes they will get accident, they might get injured, unfortunately. Yeah, but at least it's not going to fall down. You can see this accident on the bottom left-hand, bottom right-hand corner, the disaster in there. In addition to that, on the top of the bridge, we have this one to contain the vehicle, of course we need, and then the bottom, we provided them. You can see one in the bottom middle picture with the red mark up there. There are columns right in the middle, we put this barrier. If similar thing happen, like if someone go and crash to this column, the whole bridge will collapse, right? Yeah, you have to protect that one. So bridge barrier is doing a very important role in a bridge. Yeah. The reason I put this one in here, I will go back to all my slides. The time I spent nearly 2 hours talking to you. When you design a bridge, you need to think about construction. In addition to that, you saw the heavy equipment, heavy gantries, the formwork system, the way the people work, they put their lives in danger all the time. So you, as a designer, you need to keep that one in mind all the time. When I'm designing a thing, it should be able to build in a safe environment, right? Another thing, the bridge barrier thing, I should say the bridge barrier is the most difficult thing to build on a bridge. It's time consuming. You can't, there are people try so many different ways to improve the efficiency of that one. Still, they are still struggling. One reason, the bridge barrier has to build perfectly. You can't do mistakes with that one. Yeah, I'm not going to go that one in detail. Yeah, you need to build for very small tolerance in the side. Another thing, it need to follow after you build the bridge, you can't get exact shape, because the bridges, girders, pre-stressed girders, you know that one, creep shrinkage, they got a cambers, and then you can't have a uniform deck surface, but you have to overcome all these things when you are building the bridge barriers. That's what I said, it's very difficult to build. with my own experience, it's really it's time consuming. It's time consuming. Most of the bridge projects, they delay. So some reasons they delay the bridge project, but most of the time is because of the barrier construction. The next slide, how are we going to select, what are the type of bridge girders we have? We have a concrete one, we have a concrete with railing, and we have a wire rope. We don't use that one in bridge, it's not common. Yeah, how we select a bridge? Because when we select the bridge, any engineering design is based on the risk. You have to, it's a risk-based approach. Then, yeah, it's quite obvious. The amount of traffic on the bridge is one factor. And so another factor is you drive in on the same direction, or you are driving on a opposite directions, or like in this picture on the bottom, is it divided or not? It's all about the risk. If you are driving in opposite direction, there is a possibility that when you hit something and you can affect the other person as well, because there's a one risk. Another thing is a gradient of the bridge. Yeah, you know that if you are going uphill, there's a low chance you're going to go and hit a barrier at the edge, right? But you are going downhill, there's possibilities higher. And the curvature, if you're driving a straight line against the curve, you can see this in this picture, the curve here, curvature. Another thing, drop height. It's quite obvious. You saw the previous pictures, like if it is in the same level on the road, and if it is a hit the barrier, if it's topple low, is go and hit another underground road or person, or at least if it is drop from the height, I think especially the people in the vehicle will die. Another thing, in the bridge, the distance from the lane to the barrier we call the shoulder, that these road designers have for many reasons. That shoulder width is important. Wider the shoulder width, you have a time to, if you just while you are driving, if you are talking to a phone while something happened, and then if you just try to go away, you can come back to your lane again. The wider the shoulder width is better. Yeah, this is one factor we consider. Another thing, of course, the speed of the vehicle. The possibility you are driving 20 kilometers per hour in a traffic versus you are driving 100 kilometers per hour in a motorway without any traffic. So hitting a barrier, the possibility higher the speed is more. Another thing, of course, is the percentage of vehicle. The reason is if you are just driving a car, is go and hit a barrier, any type of barrier can absorb that force, but it's totally different situation. If you saw the previous pictures, we call the percentage of heavy vehicle, that mean all the trucks. So then using those parameters, we do a risk analysis. If you go to AASHTO or Australian Standard or even the Euro code, you have this approach, risk-based approach, how you going to correlate them together and calculate this one. I think it's a function at the end of the day, this average annual, the traffic against the shoulder width, against the speed, and the percentage of heavy vehicle. There are graphs, you can select the bridge barrier performance level. The barrier, what is you need, they categorize what they call performance level. Yeah, like we get grade. When we categorize I'm talking about bridge barriers, please bear with me, it's not the road barriers, bridge barriers. The performance level, we identify low, regular, medium, and special. We're not worried about special. Most of the bridges we got regular and medium. And the way this identify, they do testing, they call barrier crash test. If someone interested, if you go to Manual of Assessing Safety Hardware, I think road authorities, they know, there are safety divisions, they know this thing inside about. They in the US, they did a lot of tests based on that. They categorize performance according to performance level. They categorize the test level, DLT, DL2, 4, 5, and 6. And then based on the test level or the performance level, they give you what sort of design force you need to design for. For example, if it's a low performance barrier, you have to design for 150 kilonewton force on the barrier. If it's a regular, it's go to 300. If you go to medium, it's 600. You can imagine if you need to contain a big truck, you have to design for larger force. It's not like you contain a small vehicle, a small car. And then again, the height of the barrier that has to be varied, because you know the car and if you go to the truck, the barrier effective height, the impact location will be different. So then you get a barrier height. When you correlate all this information, the road designers, they have other thing to get when something hit to deflect. These barriers, they got a particular shape. Yeah, they got a particular barrier shape. So this thing is all everywhere is standardized. I have in this presentation a lot of links you can click, you can find them. And then I just put this information in here, yeah, for you to just get an understanding. In addition to that, in the bridge, because we said the people walk next to the barrier. When you have a shared path, cycleway, normally for the safety reasons, we have a cycleway railing in Australia about 1.4 meters above the riding surface. We add railing and we combine those together and we design the barrier. Yeah, I'm not going to go in detail to this stuff. And then what I'm going to do, because I ask questions, you guys never answer to me. Then what I thought today I'm going to do, whether you have any idea what I talk about in the presentation, I'm going to give you questions. This answering these questions, it's up to you, and then to make your own judgment. The first one I asked, the construction of bridge barrier is one of the most difficult work in bridge construction. Do you agree or disagree? Please provide justification, right? You can say, I agree, these are the reason. I disagree, these are the reason. Yeah, both. Yeah, you don't want to agree. You can disagree, but with reasons. List at least three performance or design requirements you need to consider when you are designing and detailing bridge barrier. To answer Q2, you need to listen to bridge articulation in those slides. Yeah, you already know one we talk about, you already saw in those pictures. The other one, you have three barrier types, low, regular, medium, we talked about before. To select for following scenarios, please provide justification with your assumption. Barrier to be provided on the 300-meter long bridge on Gold Highway. This is a hypothetical, okay? I just put Gold Highway for you to get that feeling, which crosses two busy connecting roads. This looks like the pictures you saw before. And barrier to be provided 20-meter long bridge we putting across the shallow creek, right? So I want you to select the barrier. You can select any barrier, so you can justify your answer. Yeah, right? With reasons. And the other one, the question 4 I asked, if road agency asks you to identify barrier performance level on an existing bridge and give them recommendation. You already saw recently one accident was in the not many days ago in TV, right? And that place RDA asks you to do the assessment in the barrier and then give them recommendation. How are you going to do it? This is real engineering. Okay, these are not the calculation. You have to think. You need to come up with answers to this situation, how to rectify. These are engineering solutions. Yeah. How do you going to do it? What is your approach? Because I talk about all these risk assessment parameters and things, and with your structural engineering understand, yeah, you need to answer these 4 questions. If you answer this one, you can send it to me to this email address. Yeah, then I can comment on that one. anyway, in the next presentation, I will give you the answers. And if you are sending me an email, just put bridge design series barrier in as the in your subject. Yeah. Then,
hi,
yeah.
Rohit. Could I ask a question? This
Yeah.
Chanaka Gunasekara.
Hi, Chanak, how are you?
Good, good.
Yeah.
Just a question on one of your earlier slides. You showed
Yeah.
the 2-meter diameter piles and
Yeah.
a 30,000 kilonewton loading. Is that
Meganewton, yeah, yes.
Yeah, is that ULS or working load for those piles? And
ULS.
also,
ULS.
Okay.
Yeah.
Right. And
Yeah.
also in those piles, I think the one over the water, what do you remember the depth of the piles and what was the
The depth of the pile is
length
about
in-
65 meters. Yeah.
and the depth in the water?
Depth in the water, I think the depth in the water, that place is about 17 meters, but in Bangkok, we got about the 12 to maybe about 15, 16 meters of soft clay, like when you just leave the case and it's go straight down. I think we got a first sand layer, like from the top of the platform level to the that level is close to 30 meters. Yeah.
Right. And the other the final question on that was when the piles were poured, were they poured in segments or continuous?
No, continuous pour. Yeah.
Right. And
Yeah.
and how long did it take to do one of those piles?
Because I think before we did, because I can send you this, and I think we did a lot of testing and thing, because before we do the piling, we check a lot of things using the cameras and other thing, and then it's co-continuous. Actually, frankly speaking, I can't remember the hours.
Right.
Yeah.
Okay. That's
Yeah.
fine. I was just curious. Okay.
Yeah.
Thanks.
But some of the piles, we have some issues actually when we do testing, integral test and other thing, because of this continuous construction, they did in one go, because the construction, the method is you just put the case in and then auger down that one and fill with the bentonite, and then they pour the concrete, flush out the bentonite. I think then we do integrated test in the comprehensive one. It's not like a hammer test kind of a thing. The sonic logging test. I have those information. Maybe I can send it to you. And then, but some places I could remember we had like a 17, 18 meters deep from the top of the pile. So we had to drill through and grout it again. Yeah.
Okay. Thanks. Interesting. So that's the one where you put those tubes through the pile and do the testing, isn't it?
Yeah, the sonic logging. Yeah.
Yeah. We'll be interested to hear about it. Okay. I'll let you continue. Thanks.
Yeah. Thanks, Janika. Thank you so much. Any questions?
Mr. Rohit?
Yeah.
Yeah, this is Arthur from CSCC. I have a question
Yes,
with regards to the heat of hydration in piers specifically, because now sometimes we need to construct this pier, say in one go. We need to probably cast a concrete in one go for the pier. And then this can develop some temperature differentials in the core and the bottom, because the pile cap is also restrained and it's cast early. And then also that you have this piers that are, piers that will be casted later. So that causes a restraint in this direction, or that's what I have been told, in this direction. If you can see. Yeah. So how do you, so the critical would be this direction. Am I correct? Or is it the longitudinal direction?
But this column, basically the column is only 1 meter thick and is heavily reinforced. This one actually, the back then we didn't consider, because I could remember this bridge we built about 2007, I think, just before I left Bangkok. I think we consider only that footing when we cast is 21 meters wide and 25 by 4.15. I think we use a stage concrete, but this kind of a construction, we never worried about the heat hydration. I think it got a sufficient reinforcement plus the those days. I think we didn't pay much attention, but especially in Bangkok, but in Australia, we actually do heat hydration analysis plus the we come up with the special mix design. For this design, I tell you what we did, because the Bangkok is hot like in Colombo, and we mix the concrete with ice and we lowered the temperature, but we didn't notice any, because like you mentioned, because the restraint, I think we might generate crack on the top, right? The top, or we might generate crack on the bottom. We never noticed in this construction at all. Yeah.
Thank you.
Did I answer the question?
Yeah. No, I think suppose if you do have a thicker concrete element, then you would have to consider it the effects.
Yeah, of course.
Yes.
Yeah. Now we do analysis. Now, for example, if you are interested, I can send you the Syria recommendations. I have that one, even all the worksheets and thing. If you put you can do the analysis. You can see the temperature differential. Another thing, the last time in my presentation, in the last link, I gave a lot of link. If you go to one of the link, the concrete specification used in the road agency in the New South Wales, that name is a B80 specification. In that one, they said your temperature differential you had to maintain, and in the same time, in the particular concrete, you need to have a certain amount of additive like fly ash and slags and things. All these mixed designs, they given even the temperatures given, and then the durability engineers, we use a strand 7, or else we use the Syria, like you can input all those things. You can manually calculate them based on that recommendation. Yeah, you can check that one beforehand. Now we do that one. Even now, I think the Australian standard is 5100 latest revision. They limit if a concrete thickness is any member is greater than the 500 mm, you have to do this analysis. That's something. That's something.
I think that's stringent.
Yeah, so stringent. Yeah. But before it used to be 1.5, then it became 1 meter, then this one 500. But and then in addition to that, designing mix and controlling temperature. In addition to that, the special formwork system like putting polystyrenes and curing, all those things we do in the durability design. Yeah. Yeah.
Thank you. Thank you.
Yeah. I will send you that the Syria recommendation that I will share with you that information. Yeah, so then you can read through. Yeah, if you have a problem like that, you can actually come up with the mixed design for that situation. You can solve that problem. Yeah.
Thanks a lot.
Then I just try to summarize. Any more questions from any others? All right. I just quickly.
Excuse me, sir. So I'm Chattum here. There's one question in the chat.
Yeah.
Mr. Tanis want to know how pedestrian bridge varies from typical bridges in the loading perspective, especially resonance and damping due to human locomotion.
Yeah, I think yeah, that's a really good question, because the pedestrian bridges, they are slender and the longer, and then the people are walking. I think as vibrate. I think a lot of design standards now frequency ranges based on the design models, they already define. So you have to comply with that. And if she's interested, I think I can send her the FIB International. They have a document about the pedestrian bridge vibration. So if you read through that document, you can get many input, but for example, in Australian standard, it's 5100 part 2. So they clearly define what sort of frequency range we need to consider when we're designing the pedestrian bridge. So when we are designing them, so we can easily do this dynamic analysis using softwares, whatever software we are using, even the simple one now. We do dynamic analysis and then we consider that one. Did I answer? I don't know whether I answer to the question correctly.
I hope he have received his answer, but there's no reply from him.
Okay.
Thank you.
Yes, sir. Thank you so much.
Okay, no worries. Then
Yeah,
I'll jump
thank
into
you.
this one. Sorry, any questions?
Yeah, I think I have a question, Rohit.
Yes.
Yeah, I'm Ravindra here. Very often people come and ask from us to construct seamless pavements over the bridge. Like in your bridge structure, you have a run-on slab, and then our pavements come and stop ahead of the run-on slab, and we anchor the pavement, stopping any longitudinal strains coming along the road, getting transferred to the bridge deck, right? So when we construct Westlink M7 in Sydney, we adopted novel approach to design and construction of seamless pavements. So where the CRCP, continuous reinforced pavement, comes and join the abutment, bridge abutment, right? So if we were to do such thing, according, I was listening very careful to your presentation. It's very good. So we cannot simply eliminate the pavement anchor without unless you have allocated those forces in the bridge designs at the beginning, isn't it?
Yeah, that's true. And yes.
It's too dangerous to do that without consulting the bridge designer in the first place, I think. Right?
Yeah, another thing, if we just talk about the M7 in here, like X7 next door, right? So I think that one, if you look at that's a segmental box girder bridge as well. But if you see the size of the columns, they're like massive jack trees in Sri Lanka, right? Yeah, very stiff. You place your deck, that's also very stiff. It's sitting on the pod bearing. I think I'm not sure it's the fix and pin. But it's even the continuous span. I think the bridge will do not too much complex things like what you can see in this slide in here. Yeah, one in the bottom left-hand corner, because these bridges are subjected to significantly large forces. Another thing, I think, other thing like you can prepare your deck surface to generate sufficient friction to get that bonding as well.
Okay, all right. Yeah, I think next time around I'll consult a bridge designer. Right?
Yeah, that's good.
Before eliminating the pavement anchors, I think I'm a little bit worried after listening to your presentation. I mean, all of these things got to be accounted first.
Frankly speaking, actually, you made a right point, because when we were designing bridge, we never think about that one.
Okay, all right. Yeah, because there were so many requests along tunnel dives in West Connect. Some of the places they want to eliminate the anchors. So yeah, that's the reason. One,
but still, I believe I think you can prepare the concrete surface to anchor this one, because in the construction, joint construction, I think we use the the full monolithic construction, but we have a construction joint without additional reos on these locations. Yeah, we can have a separate discussion on that one.
Yeah.
Ravindra.
Yeah.
Yeah.
Other thing is the surfacing on top of the bridge. We always get questions on these things, and today you explained that it's very difficult to get the tolerances on the surface of the bridge because of the.
That's exactly right. Yeah.
I never thought about that, but yep. And we find it's very difficult to keep the surfacing because it's always subjected to various stress reversals on
That's true.
the
Temperature.
bridge.
Yeah, especially
Temperature and also the stress reversals is pavement is not on the ground where we know the behaviors, but
it's flexible.
in the bridge, flexible because hogging and sagging moments are there.
Yeah.
So the pavement layers on top, you got to be designed accordingly, right?
Yeah,
so we have so many issues. Yeah,
you will see the cracks on the, especially the bridges with link slabs. Yeah, you will see that one later on a couple of slides. I have a stress calculation actually.
Okay, all right.
Yeah.
Okay, thank you so much for today's presentation. Okay.
All right, then I will jump into this one because as I discussed before, now I'm going to summarize in the bridge superstructure performance of what we expect to have a safe driving environment and satisfy the intended functional requirement. Of course, we want people to drive in there, and the construct, operate, maintain safely. Yeah, I show you the extreme ends. The bridge construction, it should be able to safely construct, and it should be able to operate. The people should be able to drive, and the maintenance as well, because if, for example, if you use the Eiger bridges, every girder you have a 2 bearing. If you got the bridge with 12 girders, you got a 24 bearing. So then every time you need to inspect them, you have to see whether they are functioning properly or not, because if not, your bridge, the superstructure will have a problem. And another thing, environmental constraints. The one good example is the one you can see in here. We got this cable stay bridge across the river. The other one you saw previously, I discussed the balance cantilever bridge across the bridge we built. Another thing, the bridges the design should be sustainable. Now, especially the concrete mix designs, we use a lot of fly ash and slags to minimize the concrete. Minimize the cement, and the sustainable design solution, in the sense, to me, that doesn't mean you are using thin structural members, and you are reducing the member sizes to really optimize the concrete or steel. Not that you design a structure that's for example, you will see in a couple of slides, it should be provide the services that's the road authorities want us to design for, because that's where you get this one. You balancing out all the elements together in the you assemble all the element in the jigsaw, and you get the right output. Yeah, because you can interpret this one in many different ways, but to me, the engineers, we need to think, because you can't go and optimize. For example, the way that bridges are designed, I talk about, they always think they got the advantage of the flexibility in the ground, right? The soft ground, they took advantage of the fox ground. Then there is a risk as well. So then the client side as well, they need to listen to the designers. They say, I can utilize this, I can come up with this solution. They might say, no, it is not safe, that's too risky, I don't want that one. No, because that's where all this sustainability is coming into play, because you assemble each and every element together. That's the way I say it. And the functional, not functional, it should be function for indented. I will correct this one when I'm sending the slide. Function should be function for the intended design life that I mentioned before. Bridges we designed for 100 years. For example, the one on this bottom of your screen, and on the bottom of the screen on both sides, these bridges can easily last 100 years because these are monolithic constructions, and should we accommodate the climate changes? Can someone tell me why we need to, how do we accommodate the climate changes in the bridge? Can someone give me an answer to this? Simple answer. Yeah, everyday talk about.
Flooding?
One thing flooding, other one is temperature, right? The bridge is subjected to temperature, right? Go up and down. So when the heat go up, so you need to take that one into account. Like you're designing a bridge for 100 years. You are designing a bridge today, but in 50 years time, if temperatures go up by 5 degrees in average, but the temperature fluctuation, if go from 45 to 55 in a couple of days, I think at that time, this bridge won't be the last. It may have a massive impact. The flood is the major thing. I think there are not a lot of people think about temperature. That's also very important. Another one is the value for money. I put this one because the value for money in the sense, I think this is especially this need to be looked at by the road users. It's not mainly the designers. Designers can use the value for money. You get your design right. You can build efficiently and you can maintain efficiently. Yeah, that's in the same way the road authorities, their road agencies, they need to look at how much investment we're going to make, and then how much we have to allocate for maintenance, and then the other aspects as well. In addition to that, when you design this bridge, it's not a bridge, it needs to be, we talk about aesthetics, it has to be beautiful. You can see the bridge on my background. If you go to Bangkok, there's a museum they built right in middle of this one, and plus there's a very famous restaurant, actually is owned by the chief surveyor of this bridge. There's a nice restaurant around there. And then it's a very nice place to go and spend a couple of hours in the evening. They made it very beautiful. And yeah, that's that value for money, because it's not right in the surface. In that space, people can use like a park, and they can enjoy the environment. That's something, of course, we engineer not pay much attention, but we have to. Then I quickly go through this one, the bridge dimensions. I think it's designed, it's developed by our road designers, the geometric designs. Then you can calculate the lane width and the shoulder width and the barrier, of course. Yes, that's a standard for the bridge barrier. Depending on your barrier type, you need about 0.5 meter. And the cross slopes, we call the cross slope, they call super elevations. And yeah, those elements, when they tell you, then you can decide what is the width of the bridge, can work together. Yeah, there is no optimization in here, the width of the bridge. This is coming from the safety and other the geometric requirement. And when you get the width, you need to get the vertical and horizontal alignment to build the bridge. The vertical alignment, you can see these two pictures. One parameter is the flooding. The other one, of course, is the vertical clearance you need when you are building this highway, because you need the 4.4 meter clearance from the road to the soffit of your structure. So you can't design a structure with 5 meter one, or you don't want to design one with 8 meter one. So because it's no point designing. Yeah, and if you design the less than the minimum clearance requirement, there is the risk that the oncoming vehicle can hit this bridge and it can damage. If you design over height, so like more than requirements, so that means you are just increasing your the structures, the column width, heights and things, and then it will add additional cost. And then the bridge types, I think I put not go in detail in the previous. The one is a plank bridges. It's very common. The one thing I just want to note in the plank bridges you can use between span 7 meter to 20 meters. And the girder depth varies between 300 to 700. It can be designed as a composite. It can be built, placing the plank side by side, or you can space the plank. You can space the plank. The only thing you can space this plank. Even I put the maximum 400. It's for the safety other reason, but you can, even if you need, you can space the larger than that if you need. Some instances you can make it. You can make it larger. And this is a pre-stressed concrete type. The pre-stressed concrete girders, they are not reinforced concrete, and they are simply supported and placed on the elastomeric bearing. It can be connected with the link slab. I will explain it to you later, because we place these girders like the span and span. You cast the deck continuously. In that way, you eliminate the number of expansion joint in the bridge that will give you a better riding surface. So the distance between the expansion joint, you can push as long as 200, but it's recommended 120 to 150. I just iterate this one. You don't need transverse post tensioning for this post tension ties for these bridges. This is a standard practice. I use a lot in Bangkok. The Bangkok called the approach bridges. It's about 70 meters in length. The span is the total length of the approach is about 70. The span is about, the standard one is 10 meter. We always have a 7 or 6 span on either side, and we place the plank side by side, and then we put the PT bar, post tension tie bars, and then we lock them together. And we use this one in the rail bridges as well. I think the Queensland, they were using it, but I think in the good thing, I think the RMS in here, with a lot of analysis and detailing, people come up with this solution. It's really good. You can build these bridges without ties. Yeah, you can do grillage modeling and thing. We will learn it later. You can build, because this bridge, there's a lot built in here in Australia, because without this tie, because this tie is one of the most difficult thing to construct and maintain. And yeah, because even there's no guarantee with this, the fatigue and thing, they depend on the quality of the tie, you get a crack or not. Yeah, that is what I want to emphasize in this bridge design. That is one of the main advantage. You can use the plank, but without having a tension tie, it's a really good one, because I know how difficult to build this one, my experience in Bangkok. These bridges are common across the creek, like a short spans. Sometimes the local road, as mentioned, local roads and floodplains. With the floodplains, where instead of you are building a road embankment, so like example, even in the Colombo, maybe in some areas, if there's a flood prone areas, rather than building road embankment and the flooding the surroundings, you can build the bridge with the plank bridges with the floodplain. Then these bridges will be more or less acting like a culvert. Yeah, at the same time providing a road surface. Then the common type bridge, the multi-beam Eiger bridges. I think you have seen this one, Eiger bridge. The one in the top right-hand corner is the Superti bridge. The one on the bottom is the Makasan bridge. We use the Eiger. You saw the Eiger bridge construction right at the beginning. These bridges we use for 18 to 40 meter span, and the girder depth vary from 750 to 1.8 meter. I just put this number L over 20 because it's simply supported construction. And then the girder spacing, we don't go beyond 2.4 meter. There are many reasons to. The one reason is the bridge vibration and the rotations. And if you can design more than a 2.4 meter, but you need to have a more intermediate bracing, because the people think if you do a grillage model, you can go even 6.68 as long as you design that one, but that is not the case in the when the bridge is open to traffic. Sometimes there are bridges you let the 4-lane bridge, the inbound, outbound traffic, the people are stay in the traffic. For example, in the morning, you inbound traffic, you stay in the traffic. The others are driving. In the evening, go opposite direction because the people stay in the traffic, get that feeling. Because sometimes you have to stay in the traffic for the bridges more than 20, 30 minutes. That's really not convenient. This limitation it's not just pushing the boundaries and cutting a girder, coming up with the solution. That's have a lot of issues, because you can't solve that problem. To solve that problem, you have to invest a lot of money, because the running bridge you have to close, and then you have to go back and put more bracings, do all this, the bridge dynamic load testing and things. Yeah, these are pre-stressed concrete bridge. These are simply supported construction. You can see from this the girder, see from this picture, and then the supported on elastomeric bearing. But I got an opportunity to review one bridge is sitting on pot bearing. Still I can't digest that one, but yeah, supported on elastomeric bearing, which can go designed as a continuous, the link with the continuous deck, up to 330 meter we designed with a special way of bridge articulation, but preferred between 200 and 250. Yeah, but if you go beyond that one, you have to come up with a special kind of bridge articulation. If someone interested, I can help them how to do it. We already did. And as you say, substructure cost is higher, maintenance cost is higher in this type of bridge. Yeah, it's really high, because you have to replace this bearing. The substructure cost, you can see you have to build all this headstock and constructing this deck and everything is not that easy. The Super T bridges, I think in Australia, I think the New South Wales, we built the longest one, I think before Northwest Rail Links, is about 3.5 kilometer floodplain bridge. But Eiger bridges, yeah, as I mentioned, I gave you that example in the Raminta Expressway, the total length is about the 30 kilometers. And the common span for the bridges is about 33 meters, 1.5 for the Super T. But for the I-girders, I think the common span is 30 meters to go with. If you go with 35, they have to increase the additional girders. Girders from 4 to 5, we have to increase. This is what my experience, but if you do more analysis, if you come up with the 4 girders, still you can design. That is okay. And yeah, I put the construction of Super T compared to the other form of I-girders is more efficient. The reason is when you place the girders, it formed the bridge deck soffit. Because of that, it's very efficient. And I just give you a quick number crunching in here. If a width of the bridge is 14 meters, that I showed you before, the number of girders you need. If you get a 2.4 meter span, maximum spacing between the girders, 5.8 girders. You can't put 5.8, so you have to put 6 girders. Then your girder spacing become 2.33 if it is a Super T. Super T girder is the same I girder, but what you do, the I, you split the web into 2, you make like a trough. Yeah. The only thing, this girder is a little bit heavier than I girder because of the craneage you need to lift this one, the transportation and handling, and that those things is a bit difficult than I girder. I think that's why they are still in Asia. I think the Super T is not that popular, but in Australia, the Super T is the very quite popular because it's provide you the safe environment for the construction, because the safety is one of the paramount thing in our designs in Australia, because that's why the contractors and even designers prefer Super T wherever they want to use it. If you use the I girder, the difference would be the you get the, if you place the girders in the right spacing, you get a 1.165 cantilever span that is constructible plus the you will see what I'm discussing this one when you come to design the barrier impact load. You see that values vary from 500 kilonewton to 150 kilonewton to 500 kilonewton. So then you will see that this cantilever, higher the cantilever length, you get a big over the hoggy moment in your girder. Then the bridge deck design is not that easy because your deck thickness is the 200. Yeah, there's a lot of things you just need to keep that one in mind when you are designing and detailing a bridge. My advice all the time, especially I'm telling this one to young engineers, draw sketches. Draw this one on a piece of paper and do a little bit of things here and there. Think about it. Draw one diagram and then draw another one, different one. No, I don't want 6. I make it 5. Then put 5 and see what is happening. You first analyze your deck. 6 simply supported with cantilever and 5 simply supported and cantilever. See what sort of behavior you get, not for put in traffic load, just for the dead load, right? It's a uniformly distributed load. If you don't analyze, you just use charts or something, and just get that feeling before you go into complex analysis, and then go from there. That is very important. Yeah, because now we are just getting used to all the time doing calculation. I want to tell you, I was lucky enough. I got a lot of opportunities in my life to learn from so many experienced people. Wherever I go, I always work under, get experience, work around with very experienced people. You don't believe me if I tell you this whole bridge, including cable stay bridge, designed by hand calculation. I have this hand calculation with me here. Every detail, reinforcement, post tension, cable, everything calculated by hand. And people do computer modeling and everything, but just came up with the same solution. Yeah, and yeah, because now we not use that habit. Just do for fun. It's good. Yeah, otherwise you just keep running computer models and you just running Excel sheets, the Excel worksheets. Yeah, they will get bored with that one. But then the type is a segmental type box girder. I have this the manual I will share with you. That will gives you all the information you need to work with this one. You don't want to worry about to calculate this depth and all these dimension thicknesses. They provide you that one, so you can utilize them if you want to apply this one in your bridge. But please remember, this manual is developed for the AASHTO standard, but you have to modify according to the standard you use, like in Sri Lanka, for example, using the British standard and Eurocode, and in Australia we are using Australian standard. The live load on the bridges are significantly different. I will make a comparison when I'm going to discuss about the bridge loading and other thing. I will do a comparison for you to get some understanding and insight about it. This span is quite common between span 40 to 60 meters, and it can be sorry, it should be single cell. Single cell, 2 to 3 lanes it can accommodate. But if it is a multi-cell, you saw that the Panankawa Bridge twin cell can accommodate 6 lane, 27.6 meters. They employ for complex interchange construction because it's the box. It's very stiff, torsionally stiff. It's good for interchanges. It's supported on pot bearings, not elastomeric bearing, because this concrete very heavy, because you don't have a 12 because in the bridge you talk about you have a 12 girders, 24 elastomeric bearing, but you are going to replace with that one with 2 of them or 3 of them, and then you can't design the elastomeric bearing. You need to have the pot bearings, and then these are externally the post tensions. I will share with you all some sketches and diagrams and how we're going to do external post tension. Even when you read that manual, it shows. Yeah, if I just explain it to you in the mechanics, it's the simply supported beam. We have a 2-point load at the quarter point. So when you apply the PP, then your bending moment diagram, PL by 4, PL by 4 coming from at the support is 0, at the location of the load is PL by 4, then the bending moment is constant all the way through, PL by 4, then go to 0 in the other end. So this is the principle they use in when we were designing the post-tension bridges, segmental constructions. We put that post-tension in here that provide the moment in opposite direction. That's this simply supported one provides sagging bending. Your post-tension will provide hogging bending, then is balancing out. That's how they design, because they are not like the rocket science. It's very simple mechanics you learn in your unit. Yeah. And distance between EJ, you can go up to 400. That's if you use the ground flexibility. And then the otherwise the 200 to 250. These numbers are the ballpark figures, but you do your analysis depending on the situation. You can change your flexibility in the column. You can vary that one. The substructure cost is less. You saw that one. This one, no cross set, no putting, and yeah, only pile, column, and the box. The maintenance cost is comparatively less because you just have only the bearing in here to maintain. These statically placing, these bridges looks very nice, and you need the specialist contractors. Not everyone can build, and these gantries are expensive. You need to hire them. Yeah, there are places you can hire these gantries, and you need a specialist contractor. These gantries are heavy. If I give you the numbers, normally if a 40 meter span, a two span bridge, when you build, the gantry weight is close to 600 ton. Yeah, as I mentioned before, it's take long time to assemble, dismantle, transport. You need to invest a lot of money to get that one. But when you put that one on the bridge, you can keep going that one. With that, another thing, you have to build a couple of span to assemble the gantry as well. And the better riding surfaces this one provide, because it's the match cast box section we build in the site and we assemble them together. And construction staging analysis required. We saw that one before. I think you can use for as a guide American Segmental Bridge Institute handbook that I will share with you later. Yeah. And the other one, the bridge you saw many times. I'm going to talk much about that one. You saw that bridge. The box girder you can use as a simply supported. The only thing, the special thing, this one, we put the transverse post tension. Of course, you know that you can't design a reinforced concrete element with 6 meters in span, having two truck on that side. So with the barrier and weight, so because of that, you need transverse post tension in this kind of structures. Your expansion joint similar to the other one, you can go up to 400 meters. Yeah, it's all depend on the substructure condition, and the substructure cost is less. The maintenance is near minimum, and the aesthetically pleasing. Again, you need a specialist contractors. I forgot to put initial the cost of constructing this bridge is very, very high, extremely expensive. It's provide better riding surface. This one have a more construction stage in than the segmental box girder construction. I think the one point I think Arthur pointed out, because you need to worried about this creep shrinkage and the aging of this bridge is very important to look at. And you looked at the balance cantilever bridge as well. As I mentioned, they already span up to the 300 meter. This, the one you've seen in here, is 229. And the balance cantilever bridge we use across the rivers, the large waterways, and depend on the environmental conditions and the navigational requirement and other things. In addition to that, sometimes we build balance cantilever bridge across the where we need the 40-50 meter span across the where we need to have a more like a large motorways. Like when you build, if you want to go a bridge across that one, sometimes we go to balance cantilever one. It can be built as a continuous span. It's all the same. I put this one in here. I think I discussed with you issue at the stage 4, excess capacity of the bridge. That's I explained. Maybe I will somewhere I need to find those slides the way we check this bridge in some point to sort this as stage 4. I will share with you when I dig my old photos. It's almost close to 15 years ago. And yeah, I will share with you. Any questions? Previous couple of slides? No, then I will quickly run with you behavior of the bridge with link slab, because the reason I got this example, this is the very common form of construction. You see, I put those limitations. You can understand that one now. When you build the bridge deck, when you make it, we place the girders span by span. The girders are simply supported, but the bridge deck is continuous. I mentioned when we cast the deck with the girder, they will act together like act compositely, like a composite element. So then the force will be the bridge deck and the girder will act together. The simple forces in this one, we have all the time. The day you place this girder, cast the girder, the pre-stressed concrete, from that day onward, you have a creep. Then when you cast the deck on that one, you got a creep shrinkage all the time, right? You got a creep shrinkage all the time. Then you got a thermal expansion, contraction in the bridge all the time. The break-in and traction because during the traffic, right? If I get the example, this bridge, the length we need, this is built across the creek, 95 meters, right? Then this is the ballpark figures, the creep shrinkage. When you calculate, your strain is about 500 micron. We convert that one into 0.5 millimeters per meter. Yeah, that's a strain equal to 500 micron. And that one, when you will learn later, you will learn when we modeling that one, we convert that one into a temperature force, right? 0.5 millimeters per meter. Thermal expansion is 0.2 millimeters per meter. That is equivalent to temperature rise about 20 degrees. Thermal contraction is 0.15 millimeters per meter or 150 micron. That is equivalent to temperature drop of 15. Sorry, before I made a mistake, it's 20 centigrade up and 15 centigrade down. And then the braking and traction due to bridge will be acting because this bridge is sitting on elastomeric bearing. It's like a flat plate. It will move to one direction at about 40 millimeter. I just put this one right in here. Anyway, and then when I calculate the deformation numbers, right? Deformation, the creep is 24 millimeters. This is a very simple calculation because the creep in the bridge 95 meter, it's like a beam. It's maximum at the end, the minimum at the center, like if it is a straight line bridge, if we assume that one, right? So then the creep 24 millimeter, the calculation I got, this is round numbers, 24 times 95 divided by 2. 0.5 times 95 divided by 2 or 95 divided by 2, 0.5 mean divided by 2 again, 95 divided by 4. 96 divided by 4 is 24. When you round, 24. Thermal expansion 10. Then thermal contraction 7, braking and traction 40. That's the common for the bridge. Then you can see in the bracket, I have a bridge length 300 meters. The same number I calculate, creep shrinkage is 24 becoming 75. It's obvious because length of the bridge is 3 times higher. This is 30, 23. The deck, we keep it as the same. Then I just calculate at the expansion joint. This is the serviceability limit state, just the movement of the bridge. Let's calculate for 95 meters span bridge is becoming 71. The way I add up, creep shrinkage, shrink the bridge, thermal contraction, shrink the bridge, 24 plus 7. And when you are braking in one direction is moving, one way is go with the shrinkage, other way it's like opening up the gap and the other side is closing. I think you all got that plan. It's moving, opening up here, closing on the other side. That 40, when you add to that, you get a 71. And the expansion joint on the other bridge, 138. With the 300 meter span, if you go with the link slab, 138. And the closing, the contraction of the thermal expansion will increase the length of the bridge. That means if you have a joint at the back, it will close the gap, and the braking will do the same. One side it will close. Then if you add them together, 50. And if it is a long bridge, it's becoming 300 meter one, it's becoming 70. The reason I put these numbers in here, you will see the bridge articulation. Because these bridges are sitting on elastomeric bearing, you can't find a bearing that would accommodate 138 millimeter bridge is moving. To allow the bridge to move, your bearing has to deform. That shear deformation has to be 138 millimeter. If I give you round figure, to get the bearing height, you need to divide this one by 0.4. Yeah. You can't find the bearing to accommodate that shear deformation. Because of that, you can't go with the link slab solution with that solution. There's one reason. That's where the limitations come. If you want to design a bridge, you want to maximize this thing, just do the background calculation and try to get an understanding. This solution is feasible or not. It's not someone tell you this is the right one, but just check that. As I mentioned before, our barrier is monolithically connected with the bridge. Suppose the bridge length is 95 meters, you build your barrier 95, it's like a bridge deck. You can say because the bridge deck is with the link slab is 95, so my barrier also the same 95. Then you will see what happened to the barrier if you let that barrier to shrink by 71 millimeter, right? You can see what will happen to the barrier if you let that one to happen like that. That is what I told you when you were designing and detailing the barrier, you need to consider what? Exact deformation of the bridge. Then you need to select, you need to provide joints along your barrier to make sure that that could accommodate the bridge deformation because the barrier is directly attached to the bridge. I think I gave the answer to your question in that one. The other one, how are we going to design the link slab, right? Now I do a different analysis. You can see the one in here, in the blue, I said at link slab. We have a gap between the girders. Normally we put average, the nominal gap is 50, right? And the bridge we place simply supported and we cast this deck. I think the Ravinder, this one explains something explained a bit about that question you asked regarding the pavement as well. You saw the bridge movements before in here. In here, this one, you can see the axial stiffness. I compare the axial stiffness. Axial stiffness is AE over L, right? If I just cast monolithically this deck over the girder all the way, then there will be 50 gap left between the link slab length is 50 because it's a link the gap. That gap is 50 mm, right? But in bridge construction, we can't have that 50 gap. You will see in here, we have a link slab we create by debonding girder and the deck to girder and deck by providing 10 millimeter thick bitumen impregnated fiber, 10 millimeter thick fiber board, right? We debond that one together. With that debonding, the standard length 1.76. We can have a 2 meter. You will see in the next slide. If I compare the axial stiffness, if your gap is less because it's inversely proportionate your length, so then if a gap is 50 and the length, the debonded length is 1.76, you can see the axial stiffness of gap versus the length. The axial stiffness of the gap is 35 times higher than the artificially created link slab within the deck, right? So when you creep and shrink the bridge, that axial force, right, will push the bridge across, and this joint location, it will crack. Yeah, it can't tolerate that. It will crack. Yeah, that's the reason we debonded the deck over the cross beam, and then you cast your deck. And you saw in the previous slide, you can't go whatever the length you need. That's controlled by the bearing design. Yeah, these two elements combined together, you can decide up to what is the most suitable length. You can get the expansion joint in this form of bridge. And I just do another simple calc in here. My creek is 500 micron. Normally in the bridge construction, we use 40 MPa concrete. The corresponding Young's modulus is 32 GPa, or 32 kilonewton per square millimeter. And if you calculate that one, convert this one into a stress, you got in your bridge deck 60 MPa stress for creep. Thermal contraction, you got another 5. Total, you got a 21 MPa axial stress on your bridge. Right? The reason I put this number, let's say someone say, no, I don't want to have expansion joint in this bridge. I'm going to fix the bridge at the end and then I leave it in there, right? You can see if you want to design a structure like that, the amount of axial stress, the axial force this bridge will exert on the abutment structures. So these are the things you just need to keep that in mind, because there was a massive push for the people we call the integral type of bridge. Those bridges people use where the country's got extreme temperature conditions, extreme winters. Yeah, there's a reason to do that one. I will discuss a bit later, but it's not suitable for especially tropical climate like in Sri Lanka. I just want to emphasize this one. Even if you are using it, you need to think twice. Yeah, because that save a little bit of money, but it doesn't save any to me with my experience. I think the contractors complain the construction difficulties they have. Yeah, and then the performance wise, I really don't think it will make a significant difference compared to other issues you're going to face. Yeah, you can use it, but you have to carefully study that one. Any questions up to that one? This is the standard common construction type with the Eiger Bridge, because Eiger Bridge, you saw this one, the headstock shape. We place the headstock on the either side. We construct the link slab go across. In the link slab, we specially detail with the very heavy longitudinal reinforcements in the designs. And for this one, we have a transverse reinforcements as well. This is a very standard common type of detailing for the link slab in the Eiger bridges. But if you want, you can change it. Yeah, you can change this one. If you want to change the, you can come up with a different solution. If you want, you can design similar to the previous example, but then it will increase the depth of the structure, because in here the intention is to reduce the structure height. Yeah, so column height. That's why I come up with this solution. And the construction also not difficult. When you cast in the tech, you can put the plank or polystyrene. You can cast on the top. That is the gap. You don't have a massive gap. You have a small gap. The other thing, the cross beam in the bridge, that's play a significant role, especially the elastomeric bearing. You need to inspect and you need to replace those cross beams. You need to jack them. Yeah. So remember that when you're designing a bridge, you need to check while the bridge is jacking. It's up to the road authority to decide how do you want to perform that one, the bridge, because in here we design, we let the traffic on the bridge. Yeah, especially if you are consider an expressway, because people are paying toll every day. You can't close your bridge to replace the bearings. So you need to allow that one. So you need to consider traffic on the bridge while bridge is jacking. Then your position of the bearing, you are supporting the bridge from your cross beams, not from your girder. If you want, you can detail, you can have a wider headstock. You can jack from the girder as well, but it's not that economical. And the other thing, this bracing will play a significant role for the traffic load distribution and the dynamic behavior of the bridge. I knew this one from the testing it did in the Bangkok. You can see in this particular picture I put here, there are so many bracings, because the standard before our standard, we use only with the 2 end diaphragm and the 2 intermediate bracing, altogether 4. But this, after they do this dynamic testing, they notice that and some other modeling and the structural analysis need to increase. When we increase this one to 7 bracings, that improve the behavior, because they already tested and they noticed that one. And the bridge substructures, I think we discussed, we saw these pictures all together, the columns and the cross beams. I put this one for you to keep that one in mind. When you were designing bridges, it's not designed for traffic load. Yeah. You hardly hear the bridges fail due to traffic load. It's fail because of the traffic loading, not because of the weight of the traffic, but because some instances like a fatigue and other issues. But you can see what the nature can do to our bridges. And you can see on this picture is split into 2. The one on the top right-hand corner, you can see the foundation instability, and the column is rotate and the bridge is rotate. Yeah, you can ask 10 people to go and lift this one after the flood is over. It's really hard to restore this bridge rather than demolishing this one. You can see the flood will damage the bridge embankment in here. That caused the collapse of the bridge. So because of that, pay really big attention when you are when you do the flood modeling and the design. If you have to spend a bit more, be generous to do that one. That's very important. The other one is the earthquake designs. It doesn't matter in Sri Lanka. I think we don't have much earthquake, but even in Australia, we don't have much earthquake. But in recently, we got rectified one in Melbourne. Luckily, it's not where the populated area is, in an isolated place. But you can see these pictures, what earthquake can do. If you want to design for earthquake designs, the best code referred to, one of the best place doing research is New Zealand and in Japan And yeah, Ashto also, but go there. Even a good thing in the our Transport New South Wales, I think our RMS in here, when there's issues like that, they take that one in board. I could remember when the Christchurch earthquake happened immediately when we were doing a project, there is nothing in the code, but they came and asked us to implement certain detail in the piling, the pile stirrups. We need to hook that one to make sure that it won't burst. I think they just pay some attention in here and refer to those code, try to implement them. But I know when you go to construction, sometimes they don't happy with this thing. It's a bit difficult for them to build because they can't go and ask extra claim because you're not going to increase the weight of the steel. But if you properly design the bridge, you won't find this situation in this one. That's why the sustainable designs are coming from. And to me, because that's where as a designers, you need to think out of the box. I think please do that one. With foundation, I'm not going to talk about this one. We use board file, but from 600 to, you saw up to 2 meters. There was some bridge built in New South Wales with 3 meter diameter pile very recently. You can go up to that one, but there are different challenges you need to face. You can have a precast pile because we don't use for the screw pile for bridges, but we use for especially for sign structures and others. And the bridges, the articulation of the bridge, I've just touched base because I think I'm overboard about the time, but I will quickly run through this one. Bridge articulation, they allow bridge to move and rotate, affect due to creep, shrinkage, thermal, pre-stress, post-tension, the vertical loads and deform, wind, settlements, earthquake, flood, mine subsidence, construction staging, all those things allow the bridge to deform and rotate. I have one example in here. As we talk about few times, the bridges we build with the beam bridges, we supported on elastomeric bearing, but this bridge, continuous span bridge, we have a bridge at the bearing at two ends. You can see the way this bridge deforms. It's very complex, but you need to articulate them to make the bridge. Otherwise, this complex force, 3D force, will damage the bearing. And how to achieve the bridge articulation on the bridge structure? We use the bearing expansion joint. Another thing, what we call restraint block in the bridge. You saw on the abutment and the first cross section, we put the restraint block that will make sure that bridge is not move transversely. That we do. Another thing, bridge substructures and foundations we use. The classic example is that for the photograph, we get the ground condition, take an advantage and increase the flexibility. And then the common type of bearing we use, elastomeric bearing, strip bearings, the pot bearing. Pot bearing, we got few type. Pot bearing, you can have a free bearing, unidirectional fixed bearing. And this bearing, this elastomeric bearing, the carrying capacity is less, shear load capacity is less, but pot bearing, they have a massive load carrying capacity. I have some examples for you. And for the pot bearing, it can carry around 2,500 kilonewton maximum. But if you go to, elastomeric bearing, beg your pardon, you can go up to 2,500 kilonewton. But if you go to pot bearing, you can go up to 20,000 kilonewton. Yeah. We provide the expansion joints. We're going to discuss this one in detail later. In the bridge barrier, we have a joint. Those joint can accommodate 0 to 20 mm. We use this joint in the bridge approaches. And the small span bridges, we use a strip seal bearing. You saw that one in that calculation, that 95 meter, you can come up with the strip seal bearing. The other one, you can use the, if you need the larger span, you can use a finger plate. It can go up to 600. And then you can go to the you can use the modular expansion, modular type bearing for up to 2 meter movement. And if I just give the bridge abutment, I think I discussed this one before with you. We got a bridge approaches, batters, access road, and then the cover protection and etc. Again, in the bridge abutments, we provide to retain the structures, very important to the backfill and drainage and things in here. I think in addition to that, then there are various types. The bridge abutment, we got a wing wall, abutment walls, and etc. I think I discussed this one at the beginning. And then the restraint block I mentioned, we have provided in the bridge headstock. In addition to that, I think we discussed the shared path, noise fall, and other miscellaneous structures we have to design, and we attach to that one. I think that is the end of my the presentation. So do you have any questions? It's almost 3 hours, 20 minutes. Any questions?
Hello, sir.
Hello.
Sir, I'm Satmi. There are 2 questions in the chat.
Yeah.
Can you hear me, sir? Yeah.
Yeah.
One is asking, are there any thumb rules or norms to limit the deflection of bridge deck, particularly overhang of the deck? Because in BS 5400 Part 4 do not explain certain criteria for bridges.
I think the deflection limits is defined in the AASHTO. For example, in even Australian standard, the cantilever one, the deck is about the AASHTO. I think I will share that one. It's it's L over 300, and if you go to the bridge as a bridge, when we were checking the deflection, this whole bridge deck will be acting as a composite section. It's considered the deflection terms the whole bridge deformation, but the cantilever section itself is L over 300.
Mute yourself.
Yeah, okay.
Did I answer to the question? I can send that AASHTO design guideline. Can forward it to them. Any more questions?
There is
So normally
another one, sir.
Yeah.
Malit Nilanta is asking that it seems that Girders are introducing by US for curb and long span bridges. Their girder spacing seem much greater than 2.4 meters. How to determine the effect of vibration on different superstructure systems?
Yeah, this is the one thing. The difference is the different standard have a significant difference in the lie load, the design lie load on the bridges. There are reasons for different countries follow different approaches, and the only way you need to do the dynamic the load testing on the bridge when the bridge is when you let the traffic to go on a bridge, they put the accelerometers and they check the bridge vibration. Yeah, I think this limit, and the way in the AASHTO code approach, I used that one extensively when I was at Bangkok. I think they limit the bridge deflection to well over 1,800 to 1,000, but the approach is the whole bridge deck will carry the lie load in that analysis. Yeah. And that the trough girder spacing, sometimes they put more than that, but I think definitely those bridges, they can design with more diaphragms provided along the length of the girder. Yeah. To like I explained in that last side, we increased for 25-meter span, having before 4 diaphragms. In the span, it's increased to 7. That gives us the better behavior here. You can't just determine that one from a structural modeling. The reason is there are a lot of things, because we use in the design for live load model, they are not the real traffic, or they are the form of representation of those actual load in terms of the load models. But in the actual bridge construction, all these effects and the alignment, all these issues, and the way the varying surface behave and the bridge deck behave over the time, that produce the very complex behavior on the bridge. That's why we have to do the testing to determine that. Yeah. Any more questions?
That's only in the chat, sir.
If you don't have any more questions, so thank you so much. I think we will have a session 3 next week. I will email, I will share all the information in one place in a Google Drive. I will send that link. I think that with this presentation slides also I will send, but I will put everything in one place. In the next flyer, I think you will find that link in the flyer. When you click, all the information's there. Even I will put the presentation slides, then before the presentation, you can access them. Thank you so much.
Thank you very much, Rohit.
Thank you. So have a good weekend, everyone.
You
Good
too.
night.
Thank you, sir.
Thank you, Chatumi.